शुरू करो। हेलो। हेलो। হ্যালো। এই তো সাউন্ড সাউন্ড এখানে এন্টার হচ্ছে। হ্যালো। হ্যালো, চেক। সাউন্ড ঠিক আছে? হ্যালো। হ্যালো। এই তো সাউন্ড সাউন্ড এখানে এন্টার হচ্ছে। হ্যালো। হ্যালো, চেক। সাউন্ড ঠিক আছে? হ্যালো। হ্যালো। জুমে। হ্যালো। ওকে। সাউন্ড প্রুফ। দেখতে পাবি। ফ্ল্যাশলাইট ছোট। হ্যালো। 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 হ্যালো, চেক। পোডিয়াম নিচ্ছে না। হ্যালো। পোডিয়াম। 1 2 3। হ্যালো। ইউটিউব খোলা আছে? ডিলেটা। ওই জন্যই বুঝতে পারছি না যে সব ঠিকঠাক। দেখি। বেরোবো তো। ওই জন্য ফার্স্ট। সরা দাও না। ঠিক আছে, একটু হাতটা সরা। ওটা দিয়ে করে লাভ নেই, এটা দিয়ে করো। ঠিক আছে, বেরিয়ে যাও। এসকেপ তো।
হ্যাঁ স্কিপ, এটাকেও ক্লোজ করে, এটাকে ক্লোজ করে দিই। বের করি। এটা তো ওরমায় না, ওরমায় না, ইজেক্ট কর, ইজেক্ট কর। হ্যাঁ দরকার আছে, একদম দরকার আছে।
হয়ে গেছে,
তুই করে দিয়েছিস তো। কখনো আবার করে দিবি। হ্যাঁ হ্যাঁ হ্যাঁ, ঠিক আছে। আর দুটো বাকি আছে, শো বলছে ওরা। পিপিটির ব্যাপারটা দেখতে হবে কিন্তু, ইয়ে তো লাইভে লাইভে ঠিক হচ্ছে কিনা পিপিটির ব্যাপারটা। কি বললো এটা? ওটা ওটা লেটে আছে, এখানে চলে আসছে। এবার দাঁড়া, এবার হচ্ছে না। দাঁড়া, আগে দেখি এটা করতে পারছি কিনা। এই যে এটা তো চেঞ্জ হচ্ছে না কেন? এন্ড হয়ে গেল ফ্লাইটটা। এটা যদি এরম করি, এই যে এইটা কেন হচ্ছে না? ও, এটা বোধহয় সিলেক্ট করেনি। এবার হওয়া উচিত। হ্যাঁ, সিলেক্ট করেছে। আমরা এই না না, ব্ল্যাকটাতে করে রাখো, দেখতে দেখি চেঞ্জ হচ্ছে। করে রাখো। আর চেক করছি ওই স্লাইডটা চেঞ্জ হচ্ছে কিনা। লাইভটাতে, লাইভটাতে এখনো চেঞ্জ হয়নি এই জন্য। স্লাইড এন্ড করে দিয়েছে। This is on. This is on. It's on now. Like a TV switch.
A very good morning to everyone present here today. On behalf of the Geological Studies Unit, me and Audrey Shuta would like to invite all of you today to our one-day national seminar on processes shaping the Earth's crust, a national seminar in memory of Professor Dilip Saha. It is a distinct honor for the unit to host this seminar today, and we are pleased to welcome all distinguished guests, speakers, delegates, and participants to this conference. The Geological Studies Unit at the Indian Statistical Institute, Kolkata, was established in 1957, emerging from Professor Prashanto Chandra Mahalanobis's visionary belief in a deep and productive integration of statistics with the natural sciences. This interdisciplinary philosophy, strongly endorsed by eminent scientists such as Sir Ronald Fisher and Professor J.B.S. Haldane, laid the intellectual foundation for incorporating geological sciences with the Institute. A decisive impetus to this initiative came with the visit of Dr. Pamela Robinson from the University College London, which catalyzed the formation of the Geological Studies Unit. Since its inception, GSU has evolved into a nationally and internationally recognized center for teaching and research aimed at reconstructing Earth's geological history and paleoclimate through quantitative and analytical approaches. Rooted in its unique interdisciplinary origin, the unit continues to integrate geology with statistical methodologies while contributing significantly to India's understanding of basin tectonics, sedimentary environments, paleontology, and stratigraphy.
Distinguished guests, respected colleagues, and dear students, we gather today to honor the memory of Professor Dilip Saha, whose passing in June 2023 was a profound loss to the earth science community in India and beyond. A distinguished structural geologist and accomplished field scientist, he served with dedication at the Indian Statistical Institute, Kolkata, after completing his doctoral studies at the University of London. His immense contributions to the Proterozoic basin evolution, Himalayan tectonics and stratigraphic correlations, grounded in meticulous fieldwork and modern analytical tools, have left a lasting scientific legacy. Deeply committed to teaching, mentorship, and service to the scientific community, he will be remembered for his scholarly rigor, intellectual integrity, and humility. We are privileged to have among us the Honorable Director of the Institute, who was closely associated with Professor Dilip Saha. We would now request him to kindly share a few words with us.
When our seniors leave us, it is important for us to remember them in an appropriate manner. And when somebody like Professor Dilip Saha, somebody as prominent as Professor Dilip Saha leaves us, it is very, very important that we do something that is fitting for his memory. Professor Dilip Saha was several years older than me, but he has been my colleague for roughly 25 years. I have had the opportunity to know him personally on many different occasions. I used to meet him at lunch at the guest house for last 20 years that he was here when we were working on the platinum jubilee of the celebrations of the Institute. We were in the same committee, and many other committees have worked with him. There are colleagues and other colleagues, so all of them you don't remember in the same way, but Dilip Da is a person whom you can never forget. And although I do not have anything to talk about the content of the workshop that you will have today. I'm not competent to do that, but I am sure that this is a much needed event, and your presence here will provide the proper atmosphere for us to remember somebody as prominent as Professor Dilip Saha. Thank you very much, and I hope that you will have a productive one-day workshop. Thank you.
Thank you, sir. Now, it is my great privilege to introduce Shri Ashit Saha, the Director General of Geological Survey of India, a gold medalist in geology from the University of Calcutta. Shri Saha joined GSI in 1992 and has since made significant contribution in geoinformatics, mineral exploration, geochemical mapping, and natural geoscience data initiatives. With decades of distinguished service and visionary leadership, he has played a key role in strengthening India's mineral exploration and digital geoscience framework. We are truly honored to have him with us here today. I now invite Sri Saha to inaugurate this session.
Okay, so good morning, everyone, and my seniors, my contemporaries, and students, researchers. Uh, Feels great to be standing here. I I'll just make you acquainted with me, Dr. Parthasarathi Ghosh, who is been sitting in these corridors for the last, let's say, 3 decades, is my classmate. So now you can relate, right? Uh, Sense of time and space, very much needed. Oh, Professor Dilip Saha uh, taught us during our masters in the last period almost. Nowadays, you have semesters. So if you compare with that, it was almost in the last semester of our MSc. He was there with us. After we passed out our uh, master's program, both few of us came to ISI trying to get a fellowship. Partho succeeded, I didn't. That's why I'm standing here today. So it was a different trajectory for me, but I never stopped coming to ISI because of two factors. One is they were my seniors, my contemporaries, and great teachers, and also uh, cheap food was available in ISI canteen at that point of time. Very cheap. For us who used to save money by walking, this was a golden opportunity to come down here and have a bountiful. So that's how my uh, contact with Professor Saha was continued. He was here and we used to discuss things with him whenever required. I also, during my short unsuccessful tenure of research, I came here because Shomarendra Da, you must have known him. Shomarendra Da used to have a software at that point of time. That software was only available with him, which we used to use to calculate geothermobarometric calculations. So I used to come here, spend hours together. April 2023, we had a reunion in our college, Calcutta University. I shared the same table with Dilip Da. We used to call him Dilip Da. We had lunch together. We talked about what I am doing at that point of time. And then just within 2 months, something happened which we all, it's so dreadful and unexpected. It cannot be expressed in words, even today. This commemoration today will not bring back Professor Dilip Saha amongst us, but it will obviously instill in ourselves who are pursuing this quest for science, quest for knowledge. It will instill certain principles which he used to follow. I have seen him as a very straightforward person, committed to science, apparently very stern, but if you sit across the table with him, you only get enriched and enlightened. We need this type of persons very much at this point of time when all around we deal with actually people who preach something which they do not practice. So friends and young scientists, uh, it's my honest request that you, even though he is not there to mentor you, but there are many people who have come in contact with him. Try to know him, get to know him. His works are there. You can go through them. And I am at this moment heading an organization which at one point of time was considered to be the organization for doing professional geology. Over a period of time, there are many other organizations which have sprung up. And I can say that Geological Survey of India cannot claim to have the monopoly which it used to enjoy earlier. There are many private organizations, there are many PSUs, and you all know today the buzzword all over the world is critical minerals. Everybody is talking about critical minerals. Some knowingly, some unknowingly. And you all know why critical minerals have become the thing to be discussed at every forum. Every other day, in every other institute, there is a symposium or seminar happening on critical minerals and its related subjects. Last week I was in ISM. There also it was the topic, and you will find somewhere again it is being discussed. Today's topic, processes shaping the Earth's crust. We are the people who are actually exploiting or destroying the Earth's crust. And that has brought us today at some crossroads. There are, movements going on which actually wants to prevent this exploitation. The western part of the country is witnessing something like that in the form of Aravalli movement. And in many cases, all this movement, all this discussion, all this hullabaloo regarding critical minerals is also because of that fact, because it is felt that if we use critical minerals for the advanced technologies, then probably we'll be able to save the environment by utilizing clean energy. But not everybody believes in that. Just yesterday, the United States president had turned down, revoked that order of the regulations which was promulgating clean energy movement in USA. It's a situation of flux at this moment in the world, and geology and geological knowledge has become even more important for decision making at the topmost level in every country at this moment. You might perceive this as a threat or opportunity. That is up to you. Or I believe that behind every threat, there lies an opportunity. Just trying to say that it's a very nice time to find out an area where you can excel in geoscientific studies. There are a lot of things to be done, a lot of research to be done, which may not seem to be very apparent at this moment, but you may have to think a little 25 years ahead. That is very difficult. That is very difficult because we never thought that we will be carrying mobiles in our pocket, right? When we were studying, we never thought that one single device, pocket-sized device, will control our life. But today it is. So what will happen after 25 years is very difficult to say. But this mobile, this device, it has become very important for many reasons, not only because it is controlling our lives, but also because this particular device, which is all pervasive in the world today, the millions and millions of devices are there, some active, some non-active, also holds key to the usage and reusage of critical minerals. These are areas which also you can think about. You can think about this urban mining, you can think about circular economy, you can think about biomining. A time has come when the geologist has to think in a manner that let us stop degradation of the earth, but we cannot stop using metals. We cannot go back to the hunter-gatherer way. So how to get those metals? The metals which has already been extracted, can we reuse them? Whoever has started your career, think in this manner, because that is what is going to happen in future days. Oh, I have taken a lot of time. I have said so many things, and I would just like to stop by saying that I feel extremely privileged and honored to be standing in front of you, saying whatever has come to my mind, and thankful to you because you have been listening without any sound. Thank you very much. Thank you again, and let long live Dilip Da. Thank you.
Thank you, sir, for that very heartfelt introduction. We would now like to invite Dr. Shanta Saha, wife of Professor Dilip Saha, to say a few words.
Respected dignitaries and everyone present here. It is my privilege to say something about my husband, Professor Dilip Saha. Besides his contribution and achievements, he was a gentle family man to me. But he had many good qualities, so many good qualities. I can share a few with you. He maintained a regular daily routine throughout his life. May it be morning walk, exercise, food habit, study time, or rest time. I have never seen him sitting idle. He, in, it is in his, in each and every sphere of his life, he was sincere, dedicated, and dutiful. He had a keen interest in various subjects. He was fond of photography. He loved to read books on different subjects. And he also started to write his tour experiences. He used to, I have seen how much time he gave in Spain for editing each and every sentence of papers submitted for publication in a journal where he was the editor. And he used to give his valuable and logical comments on different topics. Thus, his family members also could always depend on him. In spite of his vast knowledge, he was very humble and down to earth by nature. Even I didn't know all his achievements before his passing away. I am fortunate to have him as my husband, but it is my misfortune to lose him so early. I am grateful to Geological Studies Unit of ISI and everyone involved for arrangement of this memorial seminar. And we, the family members of Professor Saha, would be really glad if you make a committee or arrange something to and we can extend our possible help to arrange an yearly memorial lecture or like that in his name. Thank you all. Regards.
We are privileged to have with us many distinguished personalities who were closely associated with Professor Shaha and shared long-standing professional engagements and personal rapport with him. We now invite Professor Shomnath Dashgupta to address the gathering on Professor Shaha's life and work.
Good morning, everybody. I shall be very brief. One of the reasons being that it is extremely difficult to talk about a younger person who left us. We had a long academic touch, academic discussions and academic collaborations, cooperations, whatever you can say, with Dilip. I think that it started way back in 1980s and continued till his untimely demise. I was fortunate to have come to ISI into 2021, and then I had a real close time with Dilip. We spent long hours discussing about different academic issues, and his knowledge was really supreme, which everyone knows here. He was a good teacher, an excellent teacher, which was appreciated and a teacher will never die. So he is very much with us through his teachings, through his students and research scholars. Now, I was looking at his publications once again over the last few weeks, and I was seeing that it's continuously getting cited even today. So it means what? It means that he's living very much and will continue to live with us through the work that he has done. So we have really, academically speaking, not lost him. He's very much with us today. Thank you very much.
May I next request Professor Abdul Motin to kindly offer his words in remembrance of Professor Shah.
Good morning, everybody. I knew Dilip Da, our beloved Dilip Da, since my student days. Actually, when he completed his MSc, we were student of MSc, a few years senior to me. We are fond of Dilip Da from our student days because not only he was a very brilliant student of our time, but we can talk on any question we had in our mind, whether it is taught in class or outside the class. We had the opportunity to discuss with Dilip Da. Then he left for his research work in England. Then he left, came back, we came closer. We discussed during that time for many, many years. I personally feel Dilip Da was an excellent field geologist. He was fond of that, particularly in the realm of structural geology. So he believed in structural geology, he's committed in structural geology, field-based structural geology. And nowadays we can see that his field-based structural geology are reducing in number. Maybe many reasons. Maybe the demand is low or like that, but he believed. And he was not proud. I have never seen he was proud or proudly presenting something. Just his wife said. But when he talked close to each other sometimes, he was really proud of his work, what he did in field. I personally believe that he was very particular in anything he did during his lifetime. Particularly, I have seen that is while editing a paper, while reviewing a paper or any problem, he was extremely particular. He was extremely particular about the language of the paper or anything. We had a long time in our university, that is University of Calcutta. He was associated, very intimately associated with that. He worked as a editor-in-chief of a journal, was published from our university, from our department. And apart from that, he was related with the PhD committees and other committees in our department. During that time, we had very close discussion. I really personally feel that I was really benefited from many discussions we had during that time. I fondly remember him, and his presence remained in my mind forever. I respect Dilip Da during that time. Still, I have the same respect when he's not with us. Thank you very much.
Finally, I invite Professor Topun Chakraborty to share his thoughts and memories with us.
Good morning, everybody. I knew Dilip Shah for a rather long time. We were in the same college, 2 years apart, in the same university. And after a few years after passing out from the university, we joined this institute, the same institute where I'm standing today, uh, with a few months gap between them. When I joined, he was not probably there. He was probably in the field or something like that. So I met him first after I joined ISI in the field. And that was a memorable occasion in my life. I have seen him extremely meticulous in all the things that he has done. I have seen him in the field with his meticulousness. I have seen his personal life, uh, whatever he did, as everybody said, similarly. After joining ISI, after some time, Dilipta rose to a height, and he was seen as one of the very powerful and extremely important person in ISI. At that time, Dilipta had a awe which probably the students would remember, that they were a little bit afraid that such a big guy, such a very busy guy. But when he came across the table, it was really excellent. Among the things that ISI had, probably geological studies unit of ISI has done, is emphasizing the field-based geological work. We don't have much instruments, rather no instruments in today's time. And field is the primary source of data that we collected. And he was one of the masters in that. Not only that, I would tell you an anecdote. He went to the field with one of the new students. He's probably now in JSI. And he reported that Dilipta took him to an outcrop, spent some 45 minutes without talking. He continuously examined the outcrop and asked the student also to examine the same section and said, "We shall talk later." After 45 minutes, he asked the student, "So, what did you see? What did you think about this outcrop?" The student was smart enough. He just retorted back, "What did you see, sir?" And Dilipda didn't rebuke him. Instead, he laughed and explained what is the importance of that particular exposure. The examination system for inducting research fellows in the geological studies unit, the type of question, the model that we follow in setting the question, was built by many people, among which Dilip Shah is one principal. And in these meetings, we always had Dilip Shah probably moderating many questions, probably encouraging others to make more conceptual questions than anything else. And that was very nice. Dilip Shah's death is something very shocking, shocking to the extent that when I, uh, in the early morning, saw the message from Amlan, I retorted back to him what nonsense you are talking about, because I was probably one of the last visitors to him in the hospital. Uh, I left him around 6:30. I talked with him. He gave me a very broad grin. I asked, "How are you, Dilipta, now?" He said, it doesn't seem everything is all right. But I said that, well, the diagnosis has been done, so you'll be okay soon. And next morning, he was no more. He will be remembered for many great achievements as a geoscientist. Whenever I go somewhere else in the conference or anything, some meeting outside this city, people will always ask me about him, about what he did, what he contributed. And that's a great privilege for this department. I think it's in the right spirit that we have organized here a memorial lecture, and this should be probably given a more permanent shape in future. Thank you very much. I wish all the success to this first seminar symposium organized on his memory. Thank you very much.
Thank you, sir, for sharing your memories with us. The technical sessions will commence shortly. However, before that, high tea has been arranged outside the hall. Kindly reassemble in the auditorium at 12 p.m. sharp so that the sessions may begin on time.
Ladies and gentlemen, it is a great honor and privilege to introduce Professor N.V. Chalapati Rao, an internationally respected geoscientist and currently the director of the National Center for Earth Science Studies, Thiruvananthapuram. Professor Rao is an internationally renowned earth scientist and fellow of the Indian Academy of Sciences, the Indian National Science Academy, the National Academy of Sciences, and the Telangana Science Academies. He has made landmark contributions to mantle petrology and igneous geochemistry, particularly through his pioneering work on kimberlites, lamproids, lamprophires, and their role in elucidating the geodynamic evolution of the Indian Shield. His research has significantly advanced our understanding of the subcontinental lithospheric mantle, large igneous provinces, and crust mantle processes. Professor Rao has also served as the academic community with, with distinction in several leadership roles, including editor in chief of the Journal of Earth System Science. His outstanding scientific achievements have been recognized through numerous prestigious national and international honors, most recent, the J.C. Bose Award by the Anushandhan National Research Foundation. We are deeply honored by his presence today, and I request Professor Rao to kindly deliver his address.
Esteemed audience, it's indeed a honor and privilege to be at this institute of Prasanta Chandra Mahanalobis, C.R. Rao, who passed out are products of this institute, and more importantly, on the special occasion of Professor Dilip Saha's memorial lectures. The topic I've chosen, Professor Saha may not have worked, but as my predecessor speakers have said, he has varied interests. I'm sure that he would have liked uh, the title and the contents which would follow. To share a few things with the Professor Saha, I first got acquainted with him in 1998-99 when there was a conference at Geological Survey of India, Nagpur. In those days, I was at Indian Bureau of Mines Ore Dressing Division. Then Dr. Abhinav Roy, who was his very close friend, he introduced both of us physically, but I know Saha by his publications, and it developed into a very close friendship over the years. And because I worked a lot on the igneous activity in the Kadapa Basin, and around that time, Professor Saha and his group are very actively involved on Purana basins in general, Godavari, Pranhita Valley, and also in Kadapa Basin. Second reason, I developed a lot of rapport with him because one of Professor Saha's student is my very great friend, Mrunal Kanti Mukherjee. He's at ISM. Mrunal used to live in CPW quarters, next building, and I used to be there. Similar age group. And we used to chat in the evenings, well, walks and all. He used to talk a lot about Dilip Saha. He used to call Chellu. You know, it's very tough to work with Dilip Saha. He will check every outcrop, every strike dip. He will throw that paper out. I was very curious. Such type of person still exists. I mean, I used to think. So that's how my impression on him gathered, and it took it 8 years for me to PhD, 6 or 7 years with Professor Saha. You cannot expect. He's so meticulous, as Madam has just mentioned. He's very dutiful, and he's very concerned about every measurement. That's the impression I gathered, and respect developed automatically. And of course, he's senior, but he was very nice person, extremely humble. And we used to phone over the years, and he visited my lab at Banaras. He generated data. He used to see it. And my wife and we visited Saha's residence also a few years ago. He took us to the best sari shop, Calcutta sari shop. I mean, she also accompanied us. And I mean, we had very nice time. We miss him. But as Professor Dasgupta said, a scientist never dies. He lives through publications and citations. And Professor Saha's citations are very, very relevant. I mean, even for next decades and centuries. I just want to share a couple of his contributions which I like more. The opening and closing of Purana basins is still remains $1 million question. And Saha and his group have made a tremendous impact on this area, especially Kadapa, Godavari, Pranhita, he has made. And he also, apart from that, he did a lot of fundamental structural deformation studies. His work has shown that the Nallamalai subbasin is actually an allochthonous body. It has nothing to do with the Kadapa basin. It was amalgamated during Indo-Antarctic collision. That's what he brought out. And he has also done a lot of work on your again Kadapa basin as activities, as you can see, fundamental aspects. And also he worked on variations in your deformation patterns in Himalayas, structures. Again, Professor Saha, later on he developed a lot of interest on Precambrian ophiolites. We are familiar with Phanerozoic ophiolites, but Precambrian ophiolites like Kanigiri and all along the Eastern Ghat belt, he worked a lot and he established their field aspects, which eventually proved them to be real ophiolites, which were speculated based on petrological and geochemical grounds. And he also worked on MBT Himalayas. He has diverse interests. And one paper which he submitted to JES was on universal stage operation and all that. So he has diverse interests and is a complete earth scientist, I believe. And he also published paper on comatiates. He dated some Singham comatiates, and that paper came in Lithos few years ago. And I believe any scientist should also be looked through how much mentoring he has done. It's a fate, it's a destiny that I know three of Professor Saha's students very well. Dr. Sojan Joy, after his PhD in structures, he joined De Beers Diamond Expression Company. He is my very good friend. He is still there in South Africa. Mrunal Mukherjee, of course, at ISM. Vikas Tripathi, again, a brilliant youngster who is doing very well in GSI. And Dr. Sarbani Patranab is there, may not be a direct student, but there is no doubt that Professor Saha mentored her through her careers on interest on Purana basins. And my own student, Munmun Chakrabarti, who is in GSI, when she was doing MSc, she came to me, sir, I want to do an internship on structural geology. I asked Shaibal. Shaibal was already busy with interns. Then I approached Professor Saha. He readily took her. And she developed a lot of interest. And now she is doing PhD with me. She is going to submit in 10 days' time. And she mapped the Kunavaram complex independently. And she has come up with very new models. And she always remembers Sir Saha's mentoring. So I mentioned these people as well. So it's what I thought of Professor Saha coming here. I came only for, I mean, it's a privilege to get invited to speak on this occasion. I didn't want to miss it. So I am here for that. So coming to the topic, as I showed you, I'm going to topic on or give a talk on something which we did a couple of years ago. Super deep minerals in an eclogate xenolith from Vajrakarur field. This field is located just towards the western margin of the Kadapa basin where Professor Saha has done a lot of work. I'll come to that. And I mean, for the youngsters, this talk is mainly for the youngsters who are there. So human being is always curious to know things which he or she cannot access. And interior of Earth is certainly one thing, like outer space. So we get answers from geophysics, especially seismology, experiments conducted at elevated temperatures and pressure, we get answers. And the computational mineral physics is coming in a big way that can provide answers. And if you combine all these things with the geological samples, your deep derived magmatic rocks like kimberlites, lamproids, lamprophores, they come from depths in excess of 150 kilometers. And they are the deepest derived magmas, which we can, whose samples we can access. And also they bring up a lot of material with them, including xenoliths, peridotites, eclogites, and all that. So these provide, all of them combinedly provide us information on what exactly happens in the deeper earth. And these are some of the phase transitions you are all familiar with. As you go down, the pressure is there on the y-axis. You have depths, connotations, you have temperatures. So you have graphite to diamond transition at around 150 kilometers. Then you have coesite schistosite transition at 300 kilometers. Then you have your alpha, beta, gamma olivines undergoing phase transformations. And you would end up with your ferripericlase and MgSA perovskites. These transformations happen. How do we know that these things happen? Primarily experiments. Experiments have predicted it, but then experiments are not constrained. You need to find them in real sense, but how to do that? So we get some inclusions of these phases. Whenever we find them, we corroborate them with experiments and we take them. This is thing which happens. Otherwise, it's all indirect. And also seismologists depend a lot on these phase transitions because they interpret their seismic waves and other geophysical parameters with these phase transitions. So a knowledge of them is extremely important. So you can see the pressures here. 10 kilobars corresponds to 1 gigapascal of pressure. So this is what we understand as on today, how these transitions happen. And the diamonds are very important, not only for their commercial value, but for geologists, they are important because many of the diamonds contain inclusions. And these inclusions tell us from where diamonds come from. The contemporary knowledge tells us diamonds are sourced from the deep earth, right from the lower mantle up to the subcontinental lithospheric mantle depth, because the mineral inclusions, their pressure temperature estimates tell us from where they are coming from. And if you can date them, you have not only the time constraints as well. So this is a cross section of a hypothetical your crust mantle up to your core mantle boundary, and you can see diamonds are sourced from there. Of course, these diamonds are brought up due to mantle convection up, and your mantle plumes also can bring these diamonds to the base of the lithosphere where they get entrapped in the magmas which I mentioned and which we sample them. I always make it a point to remember the great scientists who contributed a lot to experiments, because experiments, I believe, are very important to earth scientists because we cannot create Himalayas or Aravalis, but we can do experiments to simulate how they have formed. So combination of natural and experimentation helps us in a long way. And people like Norman Bowen, father of experimental petrology, a lot of his models, phase diagrams are valid even today. None were disputed. Ted Ringwood, I believe he's the one who stands next to Bowen. And because he wrote that a very influential book on composition and petrology of Earth's mantle, experimentalist, pyrolite mantle was predicted by him, origin of Earth and Moon, all the experiments were done by him, Ted Ringwood. He was in Australia National University. Then Joe Boyd, in the later on at Carnegie Institute, Washington, especially in deep mantle rocks like kimberlites and all xenoliths. Many of the phase equilibria, the studies, they're all from his works. And finally, Peter Weil, he's still active. He's 90 plus at Caltech, and he did a lot of experiments. All of these people contributed immensely to our understanding on process which happened. And there are many youngsters around, but I have a bias, so I picked up these names who inspired us in our generation. And Jules Verne wrote a very captivating novels, and one of them is The Journey to the Center of the Earth in 1864, where he talks about a magmatic ocean, and there is a lot of water in the Earth's mantle or in the deep mantle. That's what he writes in his book, and which came up as a Hollywood movie as well. But recently, in the last decade, the evidence for this has been found because in one of the polymorphs of olivine, ringwoodite, which is a hydrous polymorph of olivine, where scientists have recovered diamonds, and in that diamonds they have recovered ringwoodite actually, which was naturally found. Ringwoodite was predicted by Ringwood and his student in 1960s. It remained as an experimental product, but the proof has come from the natural proxy that it indeed exists. So the point is, because each ringwoodite can assay theoretically up to 10 weight percentage of water molecule, it's a structural water. If you total up the entire transition zone where people think a lot of ringwoodites are there, the amount of water in the transition zone exceeds that in the present day oceans, if you calculate that way. So that's the paper which came up. Now coming to my talk, two puzzling questions are there in earth sciences, which will continue to be, probed by people in the coming generations also. When did plate tectonics begin? And how deep a subducted slab can go down? These are two questions, and people try to answer from either geophysicists or petrologists or experimentalists from their own perspective. Coming to the first question, when plate tectonics believe, this is a list of all the workers whose names are given, and they all try to address in different ways. It goes back right from Hadean, and two, even people have also talked about it started only in the Pangea formation. But the one I highlighted here is a work where they use eclogites to use as a monitor to track when plate tectonics happen. So according to that, 2.1 gigayears, oldest subduction happened. It was related to an ultra high pressure eclogite. So that's what I underlined. So eclogite can be a very good proxy to understand subduction. Just to introduce an eclogite, there are legends of metamorphic petrology. It is not meant for them. It's for just students who might have specialized, over specialized. They forget our what were taught at an MSc or BSc level. Eclogite facies is a high pressure, high temperature facies where you are not supposed to get plagioclase, and a basalt normally metamorphoses at high pressure and temperature to eclogite, and it is characterized by an omphositic pyroxene, and it is characterized by a pyropic garnet, and you can have zadiate, kyanite, rutile as other minor phases. That's what by definition. So emphosite is a solid solution between augite and zadiate, and your zadiate again in this plot you can see where it plots sodium rich alkali pyroxene. Just to bring back the basics, a paper appeared last week in geology by Michael Brown and others. They said there are eclogites and eclogites, like charnokites and charnokites, granites and granites. They came up with this title. Basically, they classified all eclogites into two types. One is the mantle-derived xenoliths, which are late Archean in age, 3 to 2.5 gigayears, or they can be even also Paleoproterozoic, 2.1 to 1.7. And they interpreted them to be detached former oceanic crust. The second group they categorized are orogenic or crustal eclogites, which are much younger, but definitely of Proterozoic 2.2 to 1.7. And they can be of 1.2 to 0.85 going into Neoproterozoic, and very rarely those which are associated with sutures and accretionary orogens, they can be much younger. So basically, they divided eclogites in all tectonic, geotectonic settings into two categories. But important thing is, both these eclogites require a subduction involvement, otherwise they cannot be generated. And this cartoon illustrates that. This is a plate tectonic cartoon. You see, you have your plumes which are rising here, this point, yeah, you have plumes. Then you have different phases, stages in the formation of eclogite, which Don Anderson has referred to as eclogitic engine. You have a differentiation formulation of accumulates at mid-oceanic ridge basalt chambers. Nibir is going to talk about next. Then you have high and low temperature alteration. Obviously, it will get a deuteric alteration. Then, as the oceanic crust gains density, it will subduct, dehydration, partial melting can happen. That is the phase 3. And the subducted slab can go up to very deeper depths. That is phase 5. And these eclogites, what our Michael Brown talked about, are shown in two regimes of associated with the exhumed orogenic eclogites, which are in shallow levels, and those which are subducting deeper parts of cratonic lithosphere. They occur as eclogitic lenses, and they wait there for some magma to bring them up or plumes to bring them up, like kimberlites and so forth. So this is the introduction I wanted to give. And eclogites have been recovered from all cratons of the world, all the shaded areas or mobile belts, they have been recovered, including from Antarctica. They have been recovered, and in India also, right from Somurari in the Himalayan region to Dharwar Craton, we find eclogites which have been recovered. And studies of the inclusions in diamonds, which I mentioned, show that there are basically two types of diamond inclusions. One is eclogitic diamond inclusion. That means that inclusion has exactly same mineralogy as eclogite. And the second one is a peridotitic inclusion, which is having a mineralogy of a peridotite. So diamond inclusions broadly can be classified into two types. So the important thing is, if you measure their carbon isotopic composition, you will find these are the diamonds from Yakutia and worldwide. The peridotitic diamonds inclusions are confined to mantle field, but eclogitic diamonds are crisscrossing the mantle field, and they are showing the crustal signature. That means there must be a crustal component, or in other words, a subducted component was involved in their genesis. Inspired by this, Shire and Richardson, who did a lifetime work on diamond inclusion, they suggested the closing and opening of oceans, which we call Wilson cycles after Tujo Wilson, started at 3 gigayears, according to them. Why? Because diamond inclusions having eclogites appear around that time. Before that, they don't appear. It could be a statistical bias, but still, nowhere in the world, people have not recovered any eclogitic inclusion younger or older than 3 gigayears. So many people believe, especially those who are working in diamond inclusions, that Wilson cycle or plate tectonics started from at least 3 gigayears to explain that. And how deep an oceanic plate can subduct, that's the other question I posed. Again, the answer, people, it varied. Last 50 years, it varied with time, shallow subductions, steep subductions. But direct evidence has come from again a diamond inclusion in South America. There is a kimberlite field called Juina, where they recovered diamonds. The inclusion showed nepheline, sodium-rich calcilite, which is a feldspathoid, and spinel inclusions in a diamond. To form such an assemblage, you require a breakdown of very high pressure minerals, and that can happen only at depths of lower mantle. So people think that based on this, the deep slabs can subduct as low as deep as 800 kilometers. And actually, what we are now thinking, believing in, was predicted by Ringwood again in 1970s. He talked about subducted slabs, graveyards sitting in the deep mantle, but then here it was based on experiments. He was not having a direct evidence. This is a cartoon which Ringwood thought oceanic lithosphere getting eclogetized and subducted to lower mantle, which was reproduced by Shire et al. But what I mean to say is experiments are very elegant in addressing natural problems, and we need to consider both of them together in addressing large-scale process. So with this background, we are shifting to Dharwar Craton, Kadapa Basin here, where Professor Saha did extensive work in the Kadapa Basin here. This is very, very unique basins, convex margin. And such type of basins, there are only two basins having such type of curvature, one in Canada and one in India. Otherwise, all sedimentary basins are not of this convex shape. And people think there was a meteoritic impact. There were papers was responsible for this type of shape. Anyway, so if you go, Kadapa Basin itself lies within the Dharwar Craton. So all geologists are aware Dharwar Craton is subdivided into western and eastern Dharwar Cratons. And this is based not only empirically, but based on the chemistry, petrology, seismic characters. Western Dharwar Craton has more lithospheric or crustal thickness compared to eastern Dharwar Craton. The granitoids and the green schist belts in both the cratons are different in terms of their not only their gold content, but in their geochemistry and isotopes as well. Now, this they are separated by Chitradurga shear zone and followed by the closed bed granite. Closed bed granite itself is a 500-kilometer running batholith, and people think it's a suture which joins both eastern and western Dharwar Craton. Now, how it is formed is a question, but contemporary models show that there was a subduction of western Dharwar below the eastern Dharwar in the New Yorkian time, and perhaps closed bed granite is the resultant of it. Of course, there are opposite views also that eastern Dharwar has subducted below western Dharwar, but majority of the people believe western Dharwar subducted, especially Chadwick and many people. Of course, the polarity of subduction is an open question, but the point is all of them believe subduction happened, resulting in your closed bed granite. And the type of granitoids which you find in eastern Dharwar Craton, we collectively call Dharwar batholith. It shows an island arc type of signature. So these are the things which are the basic geological things. Now we are going to the yellow star, which is located there. Now during COVID time, a postdoc joined from me, with me. He did PhD in Japan, Amitava Chatterjee. Then we thought we should work on another site in Bolangir. But due to COVID, we could not go to field. Then he said, sir, my time is getting wasted, what to do? Then I said, I have a lot of eclogites which I collected almost 15, 20 years ago. I didn't work on them. You better start working on them. So lab is open, you start working on them. So he started working on eclogites recovered from a kimberlite called Kalyandur kimberlite. You know, towards the western Dharwar Craton, there are hundreds of kimberlites, and the field is called Vajrakarur kimberlite field, and some of them are diamondiferous as well. So in that Vajrakarur kimberlite field, there is a small cluster called Kalyandur, which is shown in dotted lines, you can see. So in one of these kimberlites, these eclogite xenoliths, Amitava started working. So this is how an eclogite in thin section scale it looks like. Very coarse grained mineralogy, and you can make out without seeing under microscope, you can demarcate the textural aspects and garnets and all caliphytic rims. And regarding Kalyandur eclogites also, when our work was started, already two papers were already published. One by my own former PhD student Ashish Dongre in Geochemica, Cosmochemica. So, and also another by S.C. Patel from IIT Bombay in Mineralogy, Petrology. Both of them have suggested these eclogites were recovered from 5 gigapascal depth ranges. I mean, that's what the conclusion of their papers, and both of them suggested that they undergone subduction. That's what the thing. So these were the eclogite samples. Amitava started working. He is now a faculty member at Pondicherry University, Amitava Chatterjee. So these are the eclogites. We have found garnet, obviously, rutile, kyanite. So while working on probe, one day he came running to me and said, "Sir, I found a lot of silica in these eclogites." I said, "You can't get quartz in eclogites. It's not possible. So the silica definitely will not be quartz unless it is contaminated. So it could be coesite. Coesite is a silica polymorph, which is a much high pressure, but EPMA cannot tell you or whether it is your coesite. We need to go to XRD to understand it. Then he also found a garnet which is anisotropic. It shows all the characters of an garnet, but still it is weakly anisotropic. We could not understand what it could be. Then, of course, we chemically from microprobe, we know it's a garnet. When we calculated formula, it is showing excess silicon. Then we thought it could be a majorite. Majorite is a type of a garnet, high pressure garnet, where silicon exists in two coordinations. Apart from fourfold, it can also occur in octahedral coordination, and it can be anisotropic. That's what from theoretical knowledge we gain. And then omphacite, of course, and we also found some potassic pyroxene. This is the PPL images. We named it coesite after our studies, but the practicality, you have a coesite, you have a polycrystalline quartz PCQ. That means your quartz has coesite has again inverted back to quartz while coming up in this eclogite, and this majorite here, and the normal garnet was also there. This is the microscopic pictures. So just to recapture your coesite, these are the stability field of stishovite coesite, very high pressure, very high temperature phases, and they are normally, if you find coesite and all, they are index minerals of ultra high pressure metamorphism. And now we want to do X-ray of it because it is in thin section. So in India, there are only two institutes where you can do XRD on a thin section scale to our understanding. And it was at IUAC Delhi. So Amitava went to IUAC Delhi. With some difficulty, we could get time during COVID time. And he could analyze that grain in thin section, which established the red lines are all your coesites, red bands and blue bands are quartz. And that was confirmed. It is a coesite. Then we also did Raman spectroscopy. Raman is a very powerful non-destructive technique. It again shows that we have quartz, we have coesite, and both of polycrystalline quartz very intimately associated with each other. Now, coesite is a very important. There's a paper from a group of scientists from Wadia Institute of Himalayan Geology who reported coesite in Somurari eclogites. So what they inferred based on that was the Himalayan subduction was much deeper up to coesite stability field depth than it was previously believed, because the presence or absence of a mineral can make a hell lot of difference to your stability field. So Sachan and group, Barun Mukherjee, these papers are published. So that shows the importance of coesite. And of course, coesite can also occur due to shock metamorphism, like in Lonar crater, coesite was reported. So you require very high pressures to generate a coesite. Now the garnet which I talked about, this is the EPMA data we plotted on silicon versus magnesium plot. You can see we have two types of garnet. One garnet is a classic garnet where silicon is less than 3, and the other garnet, majorite, the silicon content is shooting up. So you can see it is in excess of 3 super silicic, your garnet. And we again confirmed it from the majorite garnet data published from Raman spectrometry in literature. And we found them to exactly match with the majorites which we are talking about. Now, there are number of geobarometers which are available in literature where based on silicon content, we can estimate the pressure of the majorite. You can see here, these are in gigapascals, which these are the names of the persons who gave these barometers. We calculated all of them are going to depths ranging from 11 gigapascal to up to 14 gigapascal, 7.7. There is a lot of variation, but there is range of gigapascals which are much higher than what Patel and Ashish Dongre have inferred, because they did not find coesite or majorite in their samples. And we also found a potassic pyroxene, potassium-rich pyroxene, whose chemistry is similar to the diamond inclusion pyroxene which has been reported in literature. So we also calculated our sodium in CPX and the potassium in CPX constitute very good, again, barometers. Again, you can see about 7 gigapascal to 10 gigapascal pressure, this mineral is getting derived. So what all these things tell us? In science, you have two things. One is fact, second is interpretation or fiction, you can call. The fact is you have a majorite, you have a coesite in the assemblage, and this is the stability field of majorite. Here you can see 7.5 gigapascal. It starts your majorite and goes up to 18.5 gigapascal. And the stability field of your coesite is shown there. And the light blue and purple colors are the PTs of Dongre and Patel. So our data shows that the eclogite was sampled from far, far greater depths than what the earlier workers have suggested. But if you translate it in terms of tectonics, what we thought was our slab was subducting right up to your mantle transition zone to account for the majorite and coesite. And later on, this was picked up by perhaps some mechanism by convecting current or mantle plume, and it was brought again up, and our kimberlite magma picked up, and that's what we are seeing today. So we thought our slab went right up to your almost to the fringes of your lower mantle, and that material is what we sampled. We had great trouble in publishing this paper. Amitabh was very excited, sent to very top journals, but it could not get through because they wanted so much of isotope systematics and all that. And many people were already working, we know. We thought it's important to publish it. We publish in Geological Magazine, very reputed journal, and mantle transition zone derived eclogite xenolith in diamondiferous kimberlite based on simple mineralogical assemblage. So this what we inferred, and this subduction must have happened in Neoarchean time because Creton got stabilized by 2.5 gigayears. So the thing is, as I always tell to the young people, when we studied, we were taught about only crust mantle core, lithosphere, asthenosphere, thermal boundary layer, mechanical boundary layer. They still exist, they are still valid. But the thing is, there is a new way to look at the mantle, because mantle is not a simple system, it's an extremely complex system. You have rising plumes, descending slabs, you have huge discontinuities, you have a lot of remnants of paleoarcs. You need to consider all these things in your modeling. That's why modeling Earth's mantle, I think, is much more challenging than modeling atmosphere or ocean, because they are much simple systems compared to them. So you need to keep all these things in mind. So the finally, what as our Dr. Asit Saha was mentioning, critical minerals is a buzzword like AI, ML, but I worked for 9 years with critical minerals in Indian Bureau of Mines. In those days, they were called strategic minerals. But the point is, to be an expert in critical mineral, you need to be a mineralogist first. Otherwise, you cannot talk anything which is critical. I mean, mineralogy, there is no substitute. That's what I learned over last 30 years. 4 M's are very indispensable in tackling any research endeavor. One is the material, your sample. Second is the machine, the tool. Third is, of course, mind, and also motivation to pursue and tackle it to the best of your ability. These things help in the career. This is what I wanted to share it with the young people. And a lot of people were asking me about NSES and all. I just want to share, National Center of Earth Sciences is a 46 years old institution, started by Kerala state government in 1978. The founder director was ex-DG of GSI, Karunakaran. He was invited by the then Chief Minister of Kerala to start this institute. And this institute was started with a mandate of geoscience research for societal needs. I am not aware of any institute at those times in 70s to think in these terms. And he was the first one, in my opinion, who talked about earth system science, even when United States science education did not talk about it. Later on, CSR and all started your earth system science. You will be examined in geology, geophysics, atmosphere, ocean. But he conceived it long back. And this institute was taken away over by Ministry of Earth Sciences a decade ago. And we have some of the best of analytical facilities, which are very functional. And importantly, they are open to all. And we have scientists, students from all over India, Kashmir to Kanyakumari. And I am sure if you write, if you come, you won't be disappointed. That's what I can assure you. So you visit that institute, and I always believe youngsters should come and sit with the lab, at the lab, and generate their own data. You need not have to run the machine, but you should know what is happening. Just like don't believe any sample collected by others in the field. You must have your own sample. The same thing holds good for data also. You will get acquaintance. So I invite all of you to be there. And I should thank Trideep Mandal and colleagues at ISI for this invitation. And I should thank SCRB and all my research scholars. It is all due to all of their efforts. Whatever findings I am sharing are due to them. So thank you very much. So I'll take questions. Any questions? Yes, please.
Thank you for the presentation, sir. I have a question that how the increased silica is actually physically accommodated in garnet. That is one. Second is I saw there are two clusters, a black one and there are two red clusters. Are they different clusters or is it just a data
No, no.
gap?
The red one is a cluster of majorite. I just wanted to show it.
Okay.
The other one is the pyrope garnet. You have pyrope, but you also have majorite. But in microscope, we realized later, pyrope is a normal one, which is isotropic, but there are grains which are showing excess silica. So they must be, you see, looking at the charge and your size, they must be accommodated perhaps in alumina. I mean, that's the only one which comes to my mind. Or it may, calcium it cannot accommodate. I think alumina could be the phase where it was accommodated.
And
Yeah.
sir, is there any textural difference between these two garnets and?
No, they look identical. And the only thing is it is anisotropic weakly. If you look at very closely, it is anisotropic. So that's the only thing. Then we look through literature. You need to combine petrography, XRD and Raman, multiple techniques. Single technique won't help because they are extremely rare. That's what I think so. Okay.
Thank you, sir.
Yeah.
The excess silica that you were mentioning, the aluminium site, usually in other ferromagnesian minerals, we think of a Shermack substitution, right?
Yeah.
Garnet will not undergo Shermacks.
Right.
But could there be an equivalent of the Shermack substitution? Means not called Shermack,
Right.
because you don't have a fourfold
Right.
site like that. But an MgSi for AL type of substitution can introduce that. Do you see any excess iron or magnesium, etc., in the garnet when the silica is?
I can't recollect, but stoichiometrically, it is a perfect garnet. I mean, I can't differentiate based on others. Only silica excess. Maybe a little bit of your alumina content may have come down.
So it's Si3 or 12, right? I mean, so in that
Si3 or
case,
12.
you have more than 3 silicon.
Right, right.
And you must, what I was thinking is that if you reduce the alumina or aluminium, really, reduce the aluminium, then the cation has to also increase to maintain charge balance.
Yeah, but it is perfectly maintained. Alumina has reduced considerably. And I think there must be some substitution of
but
some
you
other.
have excess of magnesium or calcium.
I can't recollect now. I can't. I mean, I don't
I
remember.
was just wondering how the garnet achieves electrical neutrality.
Right. You are right. Right. But there must be difference. I can't recollect. I mean, I don't have the data right now, but it's there. I'll check it and I'll share.
The other thing is that it's very interesting of the eclogite coming up from the lower mantle, upper mantle boundary. I think
No, it's as I said, it's a inference. To
I-
account for it, we
it's
invoke
there.
that.
It's there.
That's it.
The
Yeah, yeah.
question is, I mean, what this is collected from what? From within the close bed granite,
No,
or
no, it's in the kimberlite itself. You see in the field, you just sample kimberlite, you get plenty of eclogites.
but the kimberlite itself, what is the existing theory? It originates from within the lithosphere, or
No, kimberlite, actually, the melting mechanism is a mantle plume. The plume can come from lower mantle. The plume brings the eclogite up. That's what we said. And it has just deposited at the base of the lithosphere,
so it's
where
two,
kimberlite again melted, brought
so
it up.
2 stages.
Stage. Yeah. That's the mechanism which we thought of to account for it.
Yeah, I can't think of any.
Yeah, I mean, that's that's why many reviewers wanted proof for it. How can that's why it was not considered in some other journals.
You have to send them down.
Huh? But the data I will share with you. I'll check. I can't recollect it. But I remember there is a thing with alumina silicon, right?
Yeah, very interesting talk. As far as I have seen, I mean, what Shaival is saying, I mean, there is a possibility that magnesium should increase, but it does not actually. Whatever analysis I have seen, this is very strange that SiO2 weight % goes to 40. That is 2% extra over the 38 that's the usual in garnet. But there is no magnesium exceeding in the other site. It's strange. Neither iron nor magnesium. You can have both FeS, SiAll or MgSiAll, but Fe content in the garnet is low as such. Yeah, so it is a strange thing in the sense that there is a charge imbalance in the sense that you have one extra positive charge. True. So I think that this is something to find out. I mean, it's a very interesting thing. Can I get raise an age-old question? So what is this source of this carbon in your diamond?
Sir, we didn't work on the diamond as such, but the source is perhaps a subduction or primordial carbon. There are two things. Primordial, the one from the solar system formation itself, the inorganic carbon, or a subducted, that could be. There are two ways to put it.
Yeah, but which one would you prefer?
Sir, I prefer subducted models because many of the diamonds, I mean, inclusion based thing, they all eclogetic ones, definitely that can be accounted by the subducted model. But when it comes to peridotitic one, unless we have a subduction, we can't have carbon there.
Yes.
So both components must be inherent in the deep mantle. That's what.
Thank you.
So I have a just quick query. You found excess silica in diamond. Did you find any silica rod in clinopyroxene or anything, any other evidences here? Because it is quite common in ultra high pressure rocks or kimberlite.
Okay.
So
no, but
yeah,
no.
yeah, these are telltale evidences. So
Right.
it's very nice. Otherwise,
no, actually, that sample is with me. We are trying to now date the rutile at NSES because there is rutile.
Yes.
We can date the rutile. We can know the age of subduction actually.
Yes.
That's what we are trying. But the laser, the size of the rutile also should correspond to the laser beam size. It is almost optimum. So Amal is giving a try. Let us see.
Thank you. Thank you.
And thank you very much.
Thank you, sir, for the very insightful talk. Now, ladies and gentlemen, it is an honor and pleasure to introduce Professor Nibir Mondal, an eminent structural geologist and professor of the geological sciences at Jadavpur University. With a distinguished teaching and research career spanning over 3 decades, Professor Mondal has served the discipline with distinction at Jadavpur University. He has also contributed to the academic community as professor at ISAR Kolkata, visiting professor at the Indian Institute of Science, Bangalore, adjunct professor at IIT Kanpur. Professor Mondal is a fellow of the Indian National Science Academy, the Indian Academy of Sciences, and the West Bengal Academy of Science and Technology. His contributions have been recognized through several prestigious honors, including the Shanti Swarup Bhatnagar Award, the J.C. Bose Fellowship, and the G.D. Birla Science Award. Internationally recognized for his pioneering work on geological structures and crustal deformation, his research has significantly advanced our understanding of the crustal processes. He has also served the scholarly community through editorial roles with leading journals including Terra Nova, Journal of Earth System Science, and Frontiers in Earth Sciences. A dedicated mentor, Professor Mondal has guided generations of students who now contribute across academia, industry, and research institutions. Please join me in welcoming Professor Nibir Mondal to the podium.
Hello.
So I begin with my heartfelt pranam to Dilip Da, because Dilip Da was one of the principal, and in mathematical language, eigen component of our small geostructural geology community. Of course, the smallness in terms of number. And Dilip Da used to guide, particularly in Kolkata activities in many ways. So in recent time, we have lost another principal component, our community, Dr. Sumit Rai. So this is how structural geology has somewhat weakened in the recent time. Anyway, we'll have to keep on moving. Now, coming to this deliberation, I was thinking what kind of topic I should choose for this program. So I looked at the title of this seminar, that's Shaping the Earth Crust. So I thought that I should choose some subject which complies with the broad theme of this today's discussion. Now, before I move on to this topic, let me speak a few words about myself. I came to Jadavpur in 1981 with the hope that I would study physics, because physics is my passion. Even today, I like physics. Unfortunately, at that time, getting an opportunity for studying physics in Jadavpur was extremely mountain-like difficult thing. I failed to get an admission. Then I thought what I can do. So I was looking at the syllabus of geology, or in our Jadavpur we call it geological sciences. I was a little bit impressed that I can get some test of physics in this subject. I got a chance to study mathematics. So I preferred to study geology at Jadavpur University. So my endeavor in the last 30 years' time to meet the test of physics in some ways. Of course, I do not do physics the way physicists do. It is far less than what they do. But in my own way, I try to extract the juice of physics in my own tests. So that's the basic motivation that has been in my endeavor. In fact, in my class teaching also, I want to transfer the test of physics the way I can. And sometimes it is a bit difficult to comply with the syllabus and etc. Anyway, so I have designed this today's course with the audience in my mind, especially young students here, that they can get that kind of physics test the way I take. That would be my basic motivation. The talk will consist of different controversies, questions, etc., centered upon very lively research taking place on mid-ocean ridge tectonics. Here, I would be emphasizing upon very recent development, conceptual development on mass dynamics, that what way mass dynamics can control the mid-ocean ridge processes. Looking at the Earth's surface topography, this is a panoramic view, very familiar to all of us. We see, long relief, this is how, and that defines, that's how we call it as a ridge. And this is a linear belt. And if we look at the kinematics of different ridges like mid-Atlantic ridge, then Indian ridge, and so on and so forth, they are classified broadly into three categories, depending upon their rates. fast, intermediate, slow. Now the question is why we divide them? Because they are characterized depending upon their kinematics in terms of not only tectonics, but also petrology. So that's why people are very much keen in understanding the kinematics of mid-ocean ridges. As I said that the talk will consist mainly of different uncertainties, questions, and unresolved things. So here, in the large part of my talk, I would try to bring you some of the existing ideas, what way people have succeeded so far. And then I'll come to mass that actually very few of us are familiar with exactly materialistic way what is a mass. And this is how we'll keep on moving on different topics, as you see. And lastly, we'll have some glimpse upon what we can do more about this MOR research. Now, we all know that mid-ocean ridges are continuously producing volcanisms and eruptions, releasing carbon dioxides into ocean waters, etc. But the main question is, what is the mechanism by which mels are produced? And more difficult questions, if mels are produced, how they make their pathways to come to accrete, to form the crust. That's the very, very difficult question, at least in regard to basic physics. Now, the standard idea is this, that decompression melting, we all know about it. So at certain depth, which I'm not making any details, but talking about the pathways, the system produces porosity itself, what we call as melt porosity. And this is how melt itself make their passages, allowing the partial melts to percolate under the buoyancy. And when they encounter the lithospheric base here plays a very, very critical role because they act as a melt barrier. And that's how they heats, and this is how they keeps on moving and accumulate. The question is to the students that, should we not ask the question that why all mets are focusing into the very narrow region, few kilometers? Of course, there are off-axis volcanism, but that are very sporadic. So this kind of theory was given by Kurtz from Oxford University. And based on different, Carburet is one of the outstanding researchers in this field. So based on the observations, as I was talking about, the characteristic of fast and slow are quite different. For example, in case of fast spreading ridges, there's a big magma pool. On the other hand, it's small, and there are also some melt seepage, which is absent here at melt lenses. So this is how melt formation patterns and their percolation varies depending upon the spreading rates. And apparently, the mid-ocean ridges are continuous the way we have seen in the panoramic view, but they are not continuous, both magmatically as well as structurally, what we call as magmatic segmentation and structural segmentation. And if we look at this EPR, specific rise, as you can see here, there are segmentation in magmatic segmentation I'm talking about, because geochemically, each segment has its own characteristic. They're not continuous. So we can see different segmentation in different orders, like as you see, first order, second order, then third order, then fourth order. Now, the basic question is how we can explain the segmentation, because if we think of simple upwelling, that how can that upwelling give rise to very thing. I will be showing more about that three-dimensional characteristics. So this is how some people try to explain the segmentation character in terms of partitioning of the melt upwelling. For example, the first order segmentation like this, that is related to the upwelling in the asthenosphere, heading to the lithospheric base, and this is how. Similarly, there are small scale convection leading to higher order segmentation. This is how people have tried to explain the origin of magmatic segmentation of MORS, but there are lots of problems here. We'll be discussing about that. Similarly, here you can see that the segmentation, the fourth order segmentation is related to, axial magma chamber. And in fact, this kind of melts being produced by decompression melting, when they start upwelling, they cannot upwell very straight manner because of the complex, porosity driven ascent dynamics. And that leads to segmentation, which I'll be detailing more. I'll come to this issue later. And this is how segmentation evolves in space and time, as you can see here. Because of time constraint, I'll not elaborate further right now. But here, there is an important point to focus upon, that if you look at the red areas demarcate only the melts that are successfully erupted to the surface. The remaining part failed to come to the surface. For example, the yellow one that is recycled, that means they come and then get back to the reservoir. Similarly, some parts get solidified at the lithospheric base. So only a very few fraction of the total melts being produced by decompression melting can reach to the surface and expose to the surface. And if we do calculate, then we can see that 80 to 90%, as you can see this curve, they get recycled, leaving only very small fraction, could be in the order of 5 to 10% that can reach the surface. So this is a very interesting, thing, that there is a huge melt production beneath the mid-oceanic ridges, but all of them are not coming up. Then what would be the consequence? If we would allow all melts to come, the rate of crust generation would be enormous. That is impossible to think of, right? So now coming to the next problem, the problem of structural segmentation of MOR. In fact, this is taught right from the undergraduate classes on tectonics, that the ridges are segmented by different structures like transform, transcurrent, and so on and so forth. But this problem is still existing, that we still do not know very clearly what makes a ridge to get segmented structurally. And there are some segments, structural segments, those are not transformed. Those are non-transformed type segments. So this is a very interesting problem in MOR tectonics, how to explain structural segmentation. And there have been lots of laboratory experiments, conceptual modeling and numerical simulations and so on and so forth. Still, we don't have very clear-cut answer to the question, what's the origin of transform fault or transcurrent fault, or different kinds of other types of structural segments. So I would pick one, Taras Geria, all of you probably know, he's a professor from ETH. He developed an idea from numerical simulation experiments that if there is a little bit of geometrical perturbation in the form of curvatures, then the curvatures will lead to instability, the way you can see here, that here, this is the curvature initially, there is a little bit instability, And finally, that leads to transform-like thing. And the cross-sectional view is there because it involves some detachment, crustal detachment to happen during the formation of these segments. So this is how he tried to explain, but this is quite specific because if we look at MORs all over the globe, we'll find whenever a mid-ocean ridge is forming, this structural segmentation starts happening. That's why we need to know, we need to explore more about the mechanics of this transformation. For example, now in the Red Sea, MOR is forming right now. And even its juvenile stage, it has started forming structural segmentation. So this is a very hardcore physics problem in earth sciences. The next problem, which is again very attractive, that there are some mid-ocean ridges that produce, very high topography, hill-like topography, the way you can see here, EPR. At some places like your Indian ridge, southeastern part, there is a depression, what we call axial valley, and somewhere it is in between. Now, this problem was undertaken for quite some time. As you can see, it is 2005. And Bach is one of the US scientists, geoscientists, who paid much attention to this problem. What makes a MOR to form axial high and some others to form axial valleys? So high versus valley becomes a tug of war in the research. And that triggered a lot of tectonic models, the way you can see. Let us not discuss individual models like your viscous drag and buoyancy-driven upheaval and bending and increase in density, flexural deformation of this lithospheric slab. So there are different things that was coined. But the problem is becomes more severe when we look at, let us first discuss, then I'll come to that one. That Bach is one of the landmark, as I said, landmark researcher in this field. So he proposed a particular type of hypothesis in his Nature paper 2005. He chose two models. As you can see here, the magmatic melt zone, which is buoyant. So buoyancy dominated model he is calling. And here it is a stretching model. So in one case, magma is flushing there in terms of melt rich zone, and that creates buoyancy more. And another case is lithospheric stretching. And here he made a very nice trick. I would call it as a trick, mathematical trick. What is that? That he coined a parameter, that M parameter, he said, magmatic parameter, that this is a ratio between how much dike is getting intruded and how much separation is taking place. So the balance between these two processes, as he claimed, to decide what kind of topography is going to happen. And here, as you can see, these are very nice in low simulations from his paper. And the first model produced this EPR-like geometry, whereas the other one is Southeast Indian ridge. The problem here, I hope all of you would agree with me that the same model is not creating axial high and axial valley. So the question is that why a single model, a unified model, is not being undertaken to explain these diverse characteristics in terms of MOR topography. That's a serious limitation, what I think, in Bach's model. So why I'm saying so, why I'm raising this issue, let us look at this MAR topography, which is segmented structurally. And if you look at the topography, across axis topography here, 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 you see there is a spectacular variation in the same region. So it is hard to accept that two kinds of models are being applied for the same range. So that's why we failed that we need to do something more to explain this kind of variation, even in the same mid-ocean region. And this is another dimension of the problem is this, that if we look at the profile, along axis depth profile, this I took from a paper in JGR, and here it is not a smooth one. There's a segment like this. So if the ridge is here, you can go like this, axial high valleys, etc. So that also needs to be addressed. So now coming to the main topic of what I coined in the beginning, that mass dynamics. That mass dynamics, why we need to consider mass dynamics here. Let us look at this basic premise in this proposition, that when melts are coming, it's not a pure melt. So whatever models that we are discussing, either they are considering solid, viscous, or melts. But the material that exists beneath any MR we talk about is a mixed, is a hybrid material. So the mechanical characteristic of this hybrid material is quite different from either solid or melt. That's why understanding the mass mechanics is very crucial in explaining the MR phenomena. So technically, magmatic mass is a solid melt system that considers appreciable amount of melts, as you can see here. And you can have a continuous gradation from here to here. So this definition I took from Spark. And the behavior of this whole system will keep on changing depending upon the melt content, which is quite understandable. So if we look at this cartoon diagram, I have already talked about the melt focusing, and this is how all melts get focused by porosity-driven flow. And this is but we should not consider this is a magma chamber. This is a massy region. So modeling of this massy region or theorizing the mass mechanics, it would be crucial to describe anything we talk about happening above the mid-ocean. That is the most critical thing we are going to discuss. So what is the physical evidence that allows us to consider the melt accumulations here? But this is not magma chamber. Even it is called magma chamber. The melt is extremely rich only in this portion. But altogether, this is a melt crystal combinations. So this kind of what they are calling AMC, axial magma chamber, occurs sporadically, and that leads to formation of this kind of features beneath the MOR. So if we look at the mechanical properties of this layer, it is quite distinct with respect to the overlying elastic crust and the viscous underlying mantle. So I would like to take you, here I am going to talk about deep physics about this problem, that how to calculate the viscosity of the mass region, what I'm calling as mass complex. This is indeed very critical thing and very difficult thing also. That it is undertaken in two steps. First is to calculate the viscosity of melt suspension. Why I'm calling melt suspension? Because melts are not pure. When they start ascending, they start crystallizing and form crystals. So melt plus crystals altogether have higher viscosity, as shown by Einstein way back 1906. So this is how, in the first step, we can calculate the viscosity of melt suspension, and then we can calculate the mass complex the way I'm talking about. So let us quickly make a journey, very quickly. So this is how melt suspension viscosity calculations is very difficult, because it depends not only crystal fraction, also their size distribution, polymodality, etc., and also strain rate. So this is how we need to calculate each of the parameter independently and find out ultimately what is the order by which the viscosity will increase. So we have calculated it and found that the viscosity of melts can go even up to 10 to the power 9 order, right? And once we do this, then we employ another mathematical approach to and this is known as mixture rheology approach, where we employ this logarithmic summation. And with all these exercise, we can calculate finally, mass viscosity up to 10 to the power 14 Pascal second. Considering that the asthenospheric viscosity is 10 to the power 19, and the melt suspension is in the order of 10 to the power 19. Here, 10 to the power 14 Pascal second, here we had, because we submitted a paper, we had a great fight with the reviewer because majority of the reviewers were quite critical about accepting this value. But we have one strength, because Professor Dan McKenzie, who is master of this research, he also showed that the viscosity of crystal plus melts can go up to 10 to the power 14. So this is how we depended the thing and we calculated the thing. Now I come to the main problem, the how to tackle this axial high and segmentation, etc. So here, this is a standard technique in computational fluid dynamics theory, that we have to deal with a number of, or a set of equations, as you see here, continuity equations, momentum equation, what some of you might be knowing as Navier-Stokes equations, and heat equations, here, as you can see here, energy equations. And we have the feedback, the way I have shown you earlier, the mass viscosity here. The problem, let us look at this figure. Here it is a solid one, and here it is a purely fluid one. So if you phase-wise, if you call it a 0 and 1, the fraction is increasing like this, right? Now, rheologically, this behaves like a fluid, and this behaves like a solid. What would be the behavior in between? Here is the main issue. So the issue is that your system is producing melts, increasing melts. So when you have melt production low, the system behaves differently as compared to when the system produces more melts. So that has to be tackled. Here is the novelty, that we have two factors. This is called source term, that here you have the flow mostly governed by Darcy's flow. In groundwater geohydrology, people use porous flow, and there the whole solid component doesn't move, and porous flow to viscous flow, there's just continuous switchover. So this is regulated by this source term. And how it is done? By taking the melt fraction, Ts is the solidus temperature, and in a liquid temperature, this is how we can calculate how much melt should be produced in a system during the ascent. So with this kind of thing, we can use this simple model, that if we look at the base where there is a decompression melting stops. So we can take this horizon as a horizon of thermal perturbations. So we provided a random thermal perturbations, of course, within two bounds, that bounds with the solidus and liquidus. And if we do this, then the system overlying it produces, small scale convections. What was proposed way back in 80s. And these streamlines, as you can see, these delineate the porous full flows, and they are occurring in a three-dimensional convection structure, what you can see here. And these red regions are regions of very high melt-rich regions. So this is how this model can fairly explain the origin of magmatic segmentation, the way we have discussed in the beginning. And this is a three-dimensional picture. And fantastically, you can see that the segments can be of different sizes. It's very small to very large, the way we see very commonly in nature. And also, the same model can be used to describe the, or to explain the discontinuity, structural discontinuity. These contours are basically, velocity field. Similarly, orthogonal segmentation, which you can compare with this one. And they are occurring in different orders. That's the fantastic outcome of this kind of theoretical exercise. And here we can generate transform form, the way you can see structural discontinuities, which Professor Tarasgede explained in terms of initial curvature. But in this kind of situation, it's a spontaneously generated discontinuities. We need not take any prior geometrical perturbations in the system. So that's the better explanation probably, but there are still problems because this kind of model explain transform faults in the order of, let's say, how many kilometers, about 20 kilometers. But in nature, we do get discontinuities covering about hundreds of kilometers, but we still cannot explain that kind of structural segmentation. So I'll take you quickly to axial topography, that problem, axial high versus axial low or valley, that was tackled by Bach in his paper 2005, Nature paper 2005. So this theoretical exercise is somewhat more complex than the previous one, that here to generate topography, we need to produce a solid elastic crust, and the melts or melt-rich massy material is creating stress to generate topography here. So let us look at the topography. So this is how the topography is being produced. When it is produced, when it is producing the system, the mass viscosity is in the order of 10 to the power 14. If we reduce this mass viscosity, let's say 10 to the power 12 or 11, then this kind of highs are completely vanishing and it is becoming more low topography. So what is the outcome? That we need not consider two kinds of model to explain axial valley or high. A single model, depending upon the mass viscosity, we can produce both the topography, and which is very common in nature. The same ridge we have the variation. So this is the model profile here. This is a high and low. But here again, I must surrender or must explicitly mention that there is a reasonable mismatch between the absolute value of the topography being created in the simulations and those observed in nature. Because in natural MORs, there are so many additional factors that can also contribute to this one. So this is how you can see that this is the nature, this is model, and as I said that there is a mismatch between the magnitude here. This magnitude is less than what you see in nature. This is another one in southwest Indian ridge valley, and also that most important outcome is this. This is the along axis topographic variation, which is fairly matching with that we observe from the model. So, and these are the different comparison. Now coming to the last point of our discussion, that what more we can do research about MOR. What I think that there are many people who have done petrological studies and topography, the way I was talking about magmatic segmentations and so on and so forth. But earthquake activities in the MOR is remarkable. And earthquake activities indicate that the stress field is not very simple uniaxial tension, because in undergraduate student, MOR is a divergent plate boundary, so there is a tensile stress. No, even it's a divergent boundaries, but the stress field is extremely complex. For example, somewhere it is a tensile stress, somewhere it is a compression, both along and across the ridge. And this is the way we can extrapolate the stress field. And this was showing the plastic stress, the way the magnitude is being shown. So to my opinion, there is a lot of scope to develop theoretical analysis based on observation, that how can we explain that complex nature of the stress field in MR, which is virtually unattempted. There have been some sporadic work, but one or two. So I think that's the very important area. Of course, there are huge things to do on MOR, but from geodynamic points of view, like in the Himalaya, many people are working on structures, etc., but there is no very concrete stress model that would be helpful in predicting, at least in a broader way, the earthquake activities. So I think that this is a important area we can work on. So I sincerely thank the Geological Studies Unit of this institute, ISI. And I feel really honored, because I rarely get invitation to give talks in different institutes. Probably I am from a state university, that's why I'm not invited. And I must cherish my own research group, which I've developed in the last 2-3 decades. And many of them have left the research group. They are going for postdocs, etc. And finally, I must show my acknowledgement who has provided me to live in geosciences. That is DST, now it is ANRF, Anusandhan National Research Foundation. I would not survive in Jadavpur without their support. Thank you very much. So if you have any queries or, yes.
So you have shown that the topographic height and load are related to the marsh viscosity.
Yeah.
So that means you have high topographic regions. You should have more phenocrystic material in basalt.
Say more olivine or pyroxene phenocryst in basalt, because that will impart the higher viscosity. And otherwise, you will see more homogeneous, less phenocrystic basalts. Does it match with the available data? This is a simple observation.
I really appreciate this question, but the viscosity of the mass is not only controlled by, as I have told you, the fraction of solid crystals in the system. It is also controlled by the solid component, like your rock masses and other things. Because what way we are calculating? We have solid asthenospheric material or lithospheric material, and in between we have crystal bearing melts. So even you have crystal bearing crystals more, but if the viscosity of the solid melt, a solid component is less, or their fraction is less, the whole bulk viscosity will be less.
Okay. I got it.
So it's a complex,
it's really fascinating.
Yes.
Thank you, sir, for your talk. I am curious to know how you differentiate or add these two values, SP and SO, in the equation. Like how you differentiate, like 15% SP or 20% SO. So the source term or sink terms that you have shown in the equation.
Here.
Yes, sir.
Okay. So here you see that SG and SD, these are two source terms.
Yes.
That you are giving input from outside. So that, for example, I'm trying to explain you. Let's say SD. That means if you are producing very low amount of mels, then the whole dynamics of the flow would be governed by Darcy's flow. So this part, because this part represents the viscous flows, so this part, the del P and mu F, this is the Laplacian velocity. This part will become less dominant with respect to this one. So this is how you can regulate now Stokes flow and Darcy's flow. And SD, if you look at the expression here, SD is a function of the mel, this one. So if you make phi is equal to 1, then SD would turn out to be 0. The entire flow would be guided by Navier-Stokes equation, that is Stokes flow. So this is how SD has to be manipulated, and this manipulation will take place through the mel fraction, and that happens automatically. In fact, this concept has been brought in from engineers' work, because they use this mechanics in soldering. When they put solders, the material remains in between solid and liquid. So Voilers and others, they used, this is called single phase idealizations, that you are treating melt and solid as a single phase in terms of continuum. So this is the way engineers tackle their problem. So we brought that kind of idea in geoscience. It's a multi-phase flow, but multi-phases are being treated as a single phase. In multi-phase, then you have to think of the boundary problem. If you have two fluid phase 1 and phase 2, because they undergo Eulerian flow, so you have to continuously define the boundary between the two flows, which is a very, very difficult thing. So that's why engineers, avoided that kind of complexity by making this single phase idealization.
I have a very simple question.
Yeah.
You are considering the viscosity change from the central part of the axis to across that. Okay. Now, along the central axis, the temperature is high. If we move away from that, the temperature is lowering. If the same melt having temperature variation, then lower temperature melt have high viscosity, higher temperature melt must have, lower temperature melt have higher viscosity, and higher temperature melt have lower viscosity. So without considering the mass, can you explain with the help of the temperature variation of the melt? That is one. Another point is, if we consider the mass, then when they are emplaced, now in case of this rock is mainly basaltic rock, or feldspars are there, inequant minerals, they must have some degree of orientation when they are emplaced. So do you get that emplacement-induced foliation or preferential alignment of the feldspar, inequant feldspar grains? If it is so, then definitely we can think that is crystal in the mass played a role in the viscosity contrast.
No, this is not the way the mechanics happens here, because this is a three-dimensional flow. This is a divergence, isotropic flow. So you cannot generate a foliations or something like that unless you have some, anisotropic flow in the system. So here what happens that if we can visualize physically that you have mass, solid component containing the mels, the bulk material is upwelling by Stokes flow. Within that framework, there is a Darcy's flow. So Darcy's flow and Stokes flow are happening together. At some point of time, because of the lowering of temperature, the mobility of the solid component gets slackened, leaving only mels to go up, and mels get segregated. And that's how I told you that segregated melt eventually focused into the Meadowsonic ring. So this is the way it happens. Coming back to your temperature thing, the temperature variation happens within two bounds, right? And here we are taking the viscosity as a function of temperature also. So that comes into the play. Now, if you cannot have temperature anomalously high, and whatever we are doing here, this is the level where decompression melting stops happening, because decompression melting cannot take place indefinite extent. At some critical depth, decompression melting stops happening and releasing melts. Then we are looking at what way that system will start playing. So here the temperature, of course, as you are saying, that viscosity will be a function. The whole mass viscosity calculations takes into account the inherent temperature of the system. Have I answered to your questions, or? Yes. Yes.
Higher the degree of temperature,
Yeah.
more magnesium content will be in the melt.
Okay.
Like in Deccan flat basalts and all,
Yeah.
you get the plume head, you get picrites.
Okay.
But does that satisfy this thing? Because there the mass is, the density is much higher of a picrite than a normal basalt.
Yeah, here the mass density or mass as a whole has some buoyancy. Otherwise, how would you expect convection to happen? And there the melts are the fraction of that, because this partial melting, they are become again more positively buoyant. And that's why melt can go on ascending in the form of channels. And this kind of idea was first given by Professor Dan Mackenzie, and he brought in idea about the compaction length, etc.
Function of a partially molten rock.
Yeah.
Journal of Petrology, 1984.
Yeah.
The question about that, actually, the compaction theory involves the grain size also, because the permeability also is affected by the grain size there. That's compaction's one of the fundamental ideas, is that you discriminate between the kinematic viscosity and the dynamic viscosity depending on the relation with the permeability. So in this equation, you're not bringing grain size into play, right, at all?
No, actually, in Professor Dan Mackenzie's, grain size doesn't come explicitly. What they are considering, what he considered, that the pores are interconnected, which will allow the melt phase to percolate. And how much porosity are present in the system, that is going to decide the compaction length. Because he has correlated compaction length with bulk viscosity. You think of sponge. You have a sponge saturated with water. Now you are compressing like this. Now if the sponge has less porosity, it is difficult to compress. So if the material as a whole incompressible, the compaction length would be infinite. Because in order to get one compaction, you'll have to have more dimension. So this is how he replaced the bulk viscosity in terms of fluid mechanics with his parameter compaction length. But grain size, of course, grain size can control the permeability. But in his analysis, he is considering the system interconnected pore spaces.
Yes, but I think where he brought it in was using the viscosity of the melt together with the viscosity of a deformable. So I think he was using the matrix.
He considered two components like ours, that he has solid component, he has taken as a solid viscosity, because solid means is not solid, it's a viscous, high viscosity solid phase. And viscosity he considered also 10 to the power 19. And then he considered melt with viscosity in the order of 10 to the power 6 or so, basalt viscosity. So this is how he combined the two.
Yes, but if I remember, the base of his compaction length, that was actually defined by, he said that it would probably be a grain size control layer, because the permeability, the bulk permeability.
No, this grain size is coming because interconnected pore space will depend upon the grain size. The way we have
partially, it is.
For example, I have shown you the modality and the grain shape. Grain shape also influences a lot. But in mathematical treatment provided by Professor Dan McKenzie, grain size does not come explicitly. Right. And he considered both the phases are incompressible. That's again a
that part. I think anyway, I will talk to you about this.
Also applicable to large scale dyeing, that's a kilometer scale dyeing.
Yes, yes, sure. Yes, it is scale dependent mechanics. In fact, Professor Dan McKenzie opened up a very fantastic, conceptual development in this thing. And this has a huge implication in pathological studies. For example, we talk about the formation of critical melt fraction, that you cannot extract melts unless it forms to a certain extent. Like your secondary recovery of petroleum, the way they face the problem. So critical melt fraction is again a very interesting thing, what he proposed the idea.
Why carbonate it's a low fraction?
Yeah. So I think that Professor Dan McKenzie should be regarded as any Nobel laureate in our geoscience. A couple of files, yes. Yes. And he has also been given knighthood also. And he is the only person who can nominate someone for a Nobel Prize, I know. Anyway, that's a separate thing, but I like his science. I'm very much motivated by his all papers. So, thank you. Thank you again, once again. Thank you.
Thank you, Professor Mundal, for your insightful talk. We now invite all participants to join us for lunch, which is being organized at the ground near the guest house. Our volunteers will guide you there. We kindly request everyone to be seated back in the hall by 3 p.m. as the second half of the seminar talks will commence promptly at 3 p.m. And to enjoy the talks by our eminent professors, Professor Shoibal Gupta and Professor Tapush Bhattacharya. Also, we request everybody to gather in front of the Geology Museum for a quick photo session before joining us for lunch. Thank you.
Hello.
Welcome back, everybody, for this post lunch session. It's my privilege to introduce our next speaker, Professor Shoibal Gupta from Department of Geology and Geophysics at IIT Kharagpur. Professor Gupta's research spans metamorphic petrology, tectonics, structural geology, and planetary geology, with a distinguished focus on the evolution of orogenic belts and dynamics of the lower crust. His work integrates structural, metamorphic, geochemical, and geophysical approaches to understand crustal processes through geological time, while also extending to planetary surface studies and terrestrial analogues of Mars. In addition to his significant academic contributions, he has been the recipient of several prestigious awards, including the Cambridge Nehru Scholarship, the National Geosciences Award, and INSA Teacher Award, and recognition from West Bengal Academy of Science and Technology. Please join me in welcoming Professor Shoibal Gupta to the podium.
Okay. Yeah, I think it's working. So, good afternoon. It is a bit of a mystery as to why, whenever I'm speaking, I seem to be scheduled immediately after lunch. But I know that it's probably a good thing for the people who are listening. So I think it enables you. It sounds nice to be able to sleep to sort of humming background, somebody speaking. So okay, so I'm going to talk about something which I like to think is quite closely aligned with what Professor Saha used to do. At least a part of it was certainly what is concerned with things that Professor Saha was interested in. And as Tridib also very kindly, when inviting me to talk here, so he actually did mention that it would be nice if I could talk about something that is related to the field. So it's a field-based problem. It is a very structural problem. So those of you who are not structural geologists might find it boring. But then, like me, if you're like me, I find most talks boring because I can't understand them. So we just pretend that we can and nod our heads from time to time, if you're not nodding off, that is. So when we talk about this, I'll just quickly take you through what the point of all of this is about. Is it's mostly about things that I don't understand or I haven't yet resolved. And it's something that I would like to understand and I'm still trying to understand. So I've always been interested with this thing that we see in the field, lineations. And ever since I began doing my PhD and started reading literature, I came across this word of stretching lineations. I wasn't very sure what this meant, but in time, as many of you who are working on structural geology would know, it's something that is considered to be quite important. Now, right this morning, I actually deleted 3 or 4 slides, which I now think I should have kept. It was mostly an introductory thing related to shear zones. But anyway, I'll try to do without them and just try to explain exactly what I mean here. Now, just as a background, I mean, I'm not trying to appear very uh, uh, knowledgeable. I'm just starting off with a loose definition of shear zones as given in the book of Peschier and Trau. So one of the most common patterns of heterogeneous deformation is the concentration of deformation in planar zones. And these planar zones accommodate movement. You assume that the walls of this planar zone are rigid wall blocks. Okay. Now, within these zones, which we will refer to as high strain zones, so the geometric displacement along these zones is supposed to be higher than in the surrounding blocks, and they commonly contain a lateral displacement of wall rock segments with respect to each other. Now this part, this is known as a shear zone. By this definition, a fault is a shear zone. One of the things that I would stress here is that whenever you have any fracture, that fracture automatically does not become a fault. Right? It's you only call or you classify or designate a fracture as a fault when there is a significant component of the movement vector, right, parallel to the fault plane itself. Unless that is the case, we don't call it a fault. Now, so this is inherent, as Bashir and Rao have described. So it's common now to treat faults as one in a gradational series of what we call shear zones now. I am going to be talking primarily, I've talked about shear zones, I'm primarily going to be concentrating on what are ductile shear zones. So if you have a ductile shear zones, this is uh, is a diagram. I'm sure it's nicked from some book. I think it's possibly the book by Hacken Fossil, maybe. I don't know. So my students do this kind of illegal stuff, but I can't remember. So anyway, but it really catches what I mean to say. So they have two blocks here that are being displaced with respect to each other, and instead of being the displacement happening parallel to a single plane, the movement is accommodated within a zone of finite thickness. So when you have this, there is a gradient in the strain, and the type of strain that you actually accommodate here has a significant component of what we call simple shear. So when this happens, this particular zone in the ductile regime, it actually develops planar features. And this planar feature is something that we refer to as a foliation. More typically, if the strain is high, we call it a myelonitic foliation. The foliation has formed, we believe, as a result of plastic deformation of minerals that are making up the rock. So when we do that, with respect to the strain field, we have an X, Y, and a Z axis. So there is a direction of shear, right? This is the displacement plane, broadly perpendicular to this particular zone. And then we consider this to be approximately parallel to the shear plane. So this is parallel to the walls of the shear zone. You can think of that. The XY myelonitic foliation, right, would be concentrated mostly in this zone, but it's present everywhere. X represents the direction of maximum elongation. Y is the intermediate strain axis. Z is the shortening direction, really perpendicular to the XY myelonitic plane. Now, what does this foliation plane in a shear zone then represent? Now, inside a myelonitic zone, the XY plane is supposed to represent the myelonitic foliation, the foliation that we call the myelonitic foliation, that represents the XY plane of the strain ellipsoid. Now, as you notice, the XY plane initially forms, if it's a completely simple shear zone with no transpressional component or transtensional component associated with it, no general shear. In that case, the foliation initially forms at 45 degrees to the shear zone walls. Okay, so and then it would keep on with increasing shear strain, with increasing movement. The foliation, once formed, would tend to rotate, and in the limit should become parallel to the shear zone wall. This limit presumably is never actually reached in nature. But if there are displacements over, large distances, then it might become very difficult to discriminate between the myelonitic foliation and the shear zone wall. Effectively, they become parallel. But theoretically, at least, the XY foliation does not coincide with the shear zone walls. And we can only assume that it has done so if the accumulated shear strain is extremely high. That is, if the two blocks have been displaced for a long distance, then the initial foliation that forms at 45 degrees will keep on rotating. And if the displacement is high enough, ultimately, we can approximately say that it's parallel to the shear zone wall. So in other words, the fabric in the shear zone itself, that is not really supposed to represent the orientation of the shear zone itself. Now, within the shear zone, you have these things called lineations. And as I said, I'm going to be talking about ductile shear zones. So in a ductile shear zone, right, you can get lineations formed by various means. The one which I think is very commonly encountered is something that is formed by the intersection of two planar fabrics. Right? Anyway, inside the field, you will get in any place that is deformed, especially when it's multiply deformed, you will get an intersection of two planar fabrics. So the lineation, two planes intersect, they'll form a line, so you'll form a lineation. You can also have crenulation lineations. It means whatever the fold of the foliation surface is crumpled, and the axis of those crumples actually define your lineation. Of course, then you can actually have stretching lineations in which you constrict the material that is there inside the shear zone from all directions so that they elongate in a particular direction only. So that really is what is a stretching lineation. So it can be defined by constricted grains. It can also be defined by grain aggregates. So aggregates of grains might actually become elongate, but they are restricted laterally. So it's just in one dimension that you have the maximum possible elongation. That also is a stretching lineation. And of course, you can have elongate grains, minerals that are elongate, amphiboles, pyroxenes, sillimanites, things like that, which are needle-shaped anyway. These elongate grains also can become parallel, defining a mineral elongation. Now, this is commonly regarded as being parallel to the stretching lineation, commonly. But my own experience tells me, and I'm not going to be talking about this today, is that this may not always be the case. And I've seen things to the contrary. However, what is important to us is that it's important to understand how this lineation in a shear zone relates to the kinematics of the shear zone. Because trying to understand how movement has taken place in a shear zone, it's important to understand the lineation, to identify the lineation, and then you reconstruct the strain field based on the relationship of the asymmetry with respect to the lineation. Now, what can this lineation then represent? What does it represent? In a shear zone, we get a lineation. What could it be? Could it be the transport direction? So when we see faults, one of the first things we study in a bachelor's first year course when we're talking about faults, etc. So in a fault plane, there's a line. That's the line along which movement has taken place. Net slip vector. That tells us that that is the transport direction. So in a ductile shear zone also, could this possibly be the case that the lineation you're seeing is the transport direction, and that is exactly what we would like to see? That is what we want to see, because that makes it easy for us to make kinematic interpretations. Does it just represent the maximum extension or stretching direction and not necessarily transport? This is also something that is commonly believed to be the case. It may or may not be stretching, right? But it is commonly assumed to be the maximum extension direction. The problem, of course, is that it could always be a pre-existing lineation. The rock may have been deformed before. It might have had a lineation before. And what if that lineation is still there? And then, of course, you have this curious case in which you have a lineation that is in no way related to any deformation that's taken place. Now, I'm not going to be talking about the last one. It's something I forgot to delete, actually. Anyway, the more important thing is that we talked about lineations in shear zones, and in all of these cases, we want to understand what the transport direction is. That is what is important. But if we want to understand it, we would like our lineation to be a stretching lineation. The question is it a stretching lineation? That's really something that has perplexed me much of my life. Now, I'm looking at lineations. This is a completely personal talk in the sense it's based on personal experience, right? And I'm going to be talking about what I've seen of lineation behavior in two specific areas, two shear zones. So more than the large scale kinematics, I'm just trying to tell you what problems I've had in trying to interpret what I saw in these shear zones. And these problems are by no means solved to me. So these are both in high grade terrains. One of these is the Bengali province and the other one is the Eastern Ghats Belt. Now, just to give you a regional idea of which places I'm talking about. So this, I hope you recognize, is peninsular India, right? And this is the part that's called the Eastern Ghats Belt. Now, if you actually take cognizance of this map, which is after Dobmar and Wright's classification of the eastern coast of India into different provinces. So the Eastern Ghats Belt is divided into several provinces, all of which are dominated by granulite facies rocks. But at the extreme northern part of the complex, right, this is here, the part that's north of the Brahmani River, there are high-grade rocks which belong to what's been classified as something called the Bengali province. South of that, all of this is the largest part called the Eastern Ghats province, a part that was reportedly linked to Antarctica sometime around 1000 MA or so. So The Eastern Ghats belt is this region. I'm going to be talking about this one first, the Rengali province here. Okay. So this is after Crow et al. 2003, who first sort of classified this as a sort of province which was not really like the Eastern Ghats province properly, and not like what he called the Shingbum province. So this is very strongly Archean. This is very strongly Neoproterozoic. This is Archean mostly, but it's younger than the Shingbum rocks, most of it. And it's got a grade of metamorphism that is actually mostly amphibolite with some green schist. It's not really got the typical green schist of this part of the Shingbum province, or the very high-grade granulites that you see in the Eastern Ghats province. And we know now that even the age dates tell us that this province seems to be somewhat different to both sides, whatever we see on either side. Now, I'm just talking about a part of the Bengali province. And this is just the easternmost part, you can say, in which it's actually bound by shear zone. So this is Shingbum province proper. This is the Eastern Ghats province. In between this particular part, this body of water is called the Rengali Reservoir. And this is why the reservoir exists is because of a dam called the Rengali Dam here. You have a shear zone here, right, along here. This is called the Kerajang shear zone. And bounding the northern part is this shear zone called the Akul shear zone, which sort of grades into a shear zone called the Barakot shear zone, which is subparallel to the Kerajang shear zone here. So this region here that is in between the two, sandwiched between Shingbum and the Eastern Ghats, this is the part that's called the Rengali province. Okay, so now one of my students who's actually did his PhD with me, and earlier I think he had worked with Professor Motin in Calcutta University. So Shurajit actually mapped this area. I think he largely did a very good job of whatever he did here. There are some modifications I think that are required here, mostly due to the positive outcrops and a sort of inaccessibility, not so much that you can't get there, but the problem is that you can't stay anywhere close. There wasn't any place really to stay here to do a more detailed map of this particular area. But this is largely correct. And this part is, we're pretty confident that it's all right. So this is the Talcher Basin, which is resting on the Eastern Ghats. And this is the Kerajang Shear Zone, as we mapped it. So it's more or less this way, straight, right? But it's not perfect in the sense the edges of the Talcher sediments actually define what this is. So there are different parts to it. So these are the lithologies that you see. And you can see that there are hornblende orthogneisses. You can see granulites. And what else is there? No, it's just switched over. Oh. Oops. Yeah. Okay. So this part is a quartzite unit, quartzite and the mica schist unit, right? That makes up most of the southern part of the belt. Now, if I look at structures in this particular region, so you can actually make out that there is actually a recumbent fold that's been refolded. And this recumbent fold that has been refolded here has created these lineations. So this is a quartzite unit. So we think of this as S0 being folded. This would be then S1, and this is S2, which is subvertical. Now, the interesting thing is that the axis of S of this fold here and this broad fold here are identical. Right? They're subhorizontal almost. So, and you can see this in cross section. You can actually see the trace of the recumbent fold here in section, and this is the upright fold here. This is the S2 axis here. So what you're seeing here essentially are refolded folds. These are in the quartzites. These are in the hornblende orthogneisses. You see the same features in the Rengali granulite as well. So we call this the D1 and D2 deformation, which essentially have collinear fold axis. I'm not calling them coaxial because that has other connotations which I don't want to get into. So if you now look at the pattern in which the foliations are, right? So these are mostly north, east, southeast, north, northwest, both of them dipping either steeply north or steeply south, right? Most in all lithologies, it's more or less like that, except the hinge regions of the fold. So you have a penetrating fabric formation, you have recumbent isoclinal folding, you get a cylindrical geometry, and it affects almost all parts of the province. Now, these very similar strain fields, I think, mostly based on the collinear axis, we think the D1 and D2 probably represents a deformation continuum. Now, the problem, of course, is that if you look at the lineations, they are peculiar in the sense that they're shallow. They're shallow, all right. So it's east-west. So you see the lineations are east and west, but they're either dipping north or dipping south. So it's not a perfectly well-behaved straight line. It's going this way, this way, this way, this way, which means that the fold axis is curved. So the fold axis itself being curved seems to suggest that D1 and D2 wasn't the end of the story. Okay, so it's a bimodal thing. So you get this, the fold axis normally when you have compressive deformation this way, we would tend to think of this as the y direction of the fold, not the x, and the vertical direction should be the direction of extrusion, the direction in which extension takes place. Now, how can you explain this? It's possible that this could be a large sheath fold, right? I'm not seeing much of it, only the ends of it. So this is the vertical extrusion direction, in which case the lineation should be subvertical. However, you don't actually see sheath folds in outcrop. You don't see them. And even in the terrain bounding shear zones where the strain is really high, you don't see any kind of asymmetry in subvertical exit sections, which you would expect if there were sheath folds going this way. You don't see anything like that. In fact, if you look at the asymmetry, most of the asymmetry is actually entirely in subhorizontal sections. And therefore, we also have together with that an evidence that there has been a later deformation. And this is in the form of a subvertical west-northwest, east-southeast trending strike-slip shear zones, these bound, these zones which are folded. And this is what these look like. So you get these dextral strike-slip zones. These are plan views, all of them. And you can see these are almost perfect dextral markers. So on subhorizontal sections, and these are absolutely subhorizontal, you see evidence of dextral strike-slip displacement at least. But you also see in between these zones, you have the quadsides, you also see evidence of buckling and extension. These do not seem to have much relationship with the earlier D1 and D2 folds. What you see are folds of this sort, right? And you also see some folds with subvertical axes in between. These and this part that you can see, you notice that there is a closure here and a closure here. This is simply telling you that the fold axis is going this way, and you've cut it through this particular section. And here, again, you see this line is actually drawn slightly incorrectly. It should be this way, parallel to the foliation. And what you're seeing here is a tension gash. And that's at 45 degrees to this particular strike. So these are all plan view things characteristic of what we call the D3 deformation. So D3 was dextral strike slip. It was on these west-northwest, east-southeast subvertical shear planes. In between them, you have zones where there is buckle folding around steeply folding axis, and you also have quartz bearing tension fractures, telling us that you indeed have a third deformation, which behaves this way. Now, the question is, the shortening structures which we saw related to D1 and D2, right? Are these related, are these only because of D1 and D2? Or is there some way in which D3 also had this transpressional component, that you actually had some compression related to D3 through the strike slip part, which actually created these folds in between. Now, you can create okay. So were these connected or were these not? So if we can demonstrate there was some kind of temporal hiatus between D1, D2, and D3, that would help us. Is there anything like that? Well, one of the things we could do is to just look at the microstructures. So if you collect these from the zones in between the high D3 strain zones, if you collect these, this is from the hinge of one of these upright folds that you saw, you see that there is no particular feature that indicates a lot of strain here. It seems to have annealed over a fabric. There is some recrystallization along here, but it's largely still not directional. You have a sort of what appears to be a quartz ribbon here. Again, these do not really indicate any specific directional alignment very strongly. However, as you go towards these bounding D3 shear zones, you suddenly begin seeing all these recrystallization features at the margins of the larger grains. And you begin to see these dextral features appearing, mica fish appearing, till ultimately within the bounding shear zones, you get what we call mylonites. So you see perfect examples of dextral strike movement. What is even more interesting is look at the quartz veins. We took a section from there, it's completely undeformed. So it's actually something that was created, this gap was created during this deformation, which suggests that precipitation took place during D3 probably, which is why it's not deformed at all. Now, so D1 and D2, it outlasted amphibolite fascist metamorphism, which is what the grade of metamorphism was estimated to be based on metamorphic assemblages, even the deformation characteristics. You have an annealed granoblastic mosaic that we saw as the hinge of the folds.
dating of these particular rocks, and these are shrimp dates, are 2.8 to 2.5 GA, right? What this means is that the lineation that we saw in most of this area was actually, that is related to D1, D2. This was a fold axis parallel lineation, and it was an S1, S2 intersection lineation. Even when the folding was going on, the lineation that is dominant is not any kind of stretching lineation. D3, which is what we are characterizing as a simple shear dominated zone. So you have shear bands, you have dynamic recrystallization, and most of this is under green schist fascist conditions. And here argon-argon dating done by some people earlier states this to be around 490 to 470. It's Ordo, I think, Camero-Ordovician age. Now, what this means is that although the area has a dominant subhorizontal lineation, we infer this to be parallel to the direction of D3 shearing, right? Because we think that the transport direction during D3 was subhorizontal. And yet the lineation that we see dominantly through the area is not related to D3. It's not the stretching lineation. It's actually the fold axis lineation, which is the Y direction. So it is curious that the S1, S2 intersection lineation and the D3 shearing transport direction, they are subparallel. And as far as we can tell right now, apart from coincidence, there's not much else that I can guess at. Let's just go to another shear zone. I'm sorry, but it's an income, it's an art film, so there's no real answer. I mean, I think it's something that's happening there, which we are going along to analyze, but it's something that we can look at. Again, let's go inside the shear zone, inside the Eastern Ghats belt. And when we go inside, so I'm going across to this little line here. This is what's called the, well, actually the lines this way, it's called the Mahanadi shear zone. So when we look at the Mahanadi shear zone, right, it just separates a northern part of the granulites from the rest of the Ghats province to the south. This is the river Mahanadi, and the shear zone is supposed to go along this particular trend. So I'm going to be talking mostly about things that you can see south of the shear zone. And if you look at a Google Earth image of the Eastern Ghats belt, you'll see lots of these regional scale lineaments, not lineations, lineaments, right? Geomorphic features that are very, very prominent. When we did a detailed mapping of this particular area around the type area for Chenapoda, which is Nayagarh. So when you look at this part here, you notice that all of these geomorphic features are actually turning. They turn from north-south orientation into this orientation to east-west, and then they begin to turn very close to the Mahanadi. They actually turn parallel to this zone. Now, these are all the locations that the student who worked on this, Shubham Bose, his area. Now, if you look at what we see there, over the area in the southern part, you see S1 and S2, as we see in most places. You see an isoclinal fold, you find a segregation bending that is the gneissic foliation, and the dominant lineation on the S1, S2 surface is an intersection lineation that I'm calling delta 2. So S1 and S2 they are transposed now. They are transposed. This is a plan view, and it's actually being transposed from this area. In an outcrop, we could actually get a part of this turning into an west-northwest, east-southeast orientation. And if you look at the S1, S2 surface, it's curved this way. So this is what happens in the vicinity of the curvature. The S1, S2 foliation looks in microstructure, it looks a bit like that. It's got garnet, got selebanite. Just to tell you that the grade is extremely high. So the S1, S2 segregation banding was created under granulite fascist conditions. Now under D3 then, if you now look at the shear zone, so this is west, northwest, east, southeast, as you can see from the cluster that you can see here. And this is a range of intersection lineations that you can actually see on the shear zone. So what is this intersection lineation that you see on the shear zone foliation? This is an intersection between the new myelonitic foliation that has developed and the older S1, S2 fabric. And it's all over the place. When you look at it, you can see the curvature in section views. So this is S1, S2 curving into the S3 planes here. And on the myelonitic foliation surface, you can see the intersection lineation. This is what we call delta 3 here. Sectional view, again, you have a top to the north, a normal sense motion here. And if you look at the high strain zones of this particular foliation, you'll actually see a proper stretching lineation in those domains. And there, the stretching lineation is absolutely clustered around these areas. So it means that what we suspect is that the intersection lineation between S1, S2 and the new foliation surface, you see that in slightly in higher strain, but not highest strain zones. And as a consequence of which, what is happening is that this intersection lineation is rotating till it ultimately becomes parallel to the extension directional that we see here. So the intersection lineation also becomes parallel in the higher strain zones. So essentially those intersection lineations that are here would rotate this way, those that are here would rotate this way. So all of these would tend to rotate towards the direction which is the inferred extension direction of L3. Inside the D3 shear zone, that is inside the shear zone that you're actually finding, you see normal sense shear in vertical section. This is the kind of microstructure that you see. Now, I'm not going into the details of the microstructure, but these tell you that although it is lower grade than granulite, nevertheless, this segregation of quartz and feldspar into separate layers would only happen under amphibolite facies conditions. Under granulite facies conditions, the competency of viscosity properly of quartz and feldspar become roughly equal. So there is not much segregation. So the segregation only takes place under amphibolite facies conditions. So once this happens, lineations actually become prominent and develop under these conditions. And this is what the stretching lineation looks like in these rocks. We did some quartz CPO analysis on this, and these indicate that you have rhomb A slip as dominant in some and basal A along others. So in all of these, when you're interpreting this, it is vital to know what you are characterizing as the X direction or the transport direction. Now this itself is complicated. It might be different. Our interpretation of what the system is might be different depending upon whether we choose X and transport to be different or the same. So it's actually important to be able to understand this, which is why this complication of lineations becomes so important. Now, if you go a little further north into the Mahanadi River, then you get this west-northwest, east-southeast tending shear zone, which is what we call the Mahanadi shear zone. And within that, the fabrics are even finer grained. And you see, this is a planar view, and it's purely dextral strike slip motion. This is actually a place where we find the older S3 fabric that is truncated by a fabric that is your characteristic of the Mahanadi shear zone, even finer grained. You have bulging recrystallization here. You see, and this is in the subhorizontal XZ section, you see silibanite needles rotated here, and you also see the quartz segregated into ribbons. Interestingly, the quartz C-axis and the sillimanites do not plot at exactly the same points. They actually are marginally displaced with respect to each other. So this D4 deformation, that of the Mahanadi shear zone, if you look closer, you will find that in each of these, you get what are called these low angle grain boundaries. So these are small displacements of the lattice structure with respect to other parts of the lattice. Only at the boundaries you get bulges forming. Ultimately, these would actually begin to form the new grains that can define a separate lineation. But as you're approaching it, most of it is still in an incipient stage. As you get closer, these become dominant and overwhelm what you're actually going to see. What this means is that if you look at the evolution from proto to ortho to ultramyelonites in this part, so we are going from the D rocks of the D3 shear zone and D1, D2 partially overprinted by D3 into D4. Then you go from a situation which looks like this with bulging just starting to appear, right? More bulges here till ultimately you land up in a region where it's completely an orthomyelonite. Now, what does this mean? If you look at this figure, in the D3 shear zone in that particular area, we had a subvertical lineation, stretching lineation, which was created by elongation of quartz grains. Now, as we imposed D4 strain, which again coincidentally was exactly at right angles to it. So the stretching direction during D4 was subhorizontal. And initially D3, the stretching action was downward. So what you will see is that you'll see the length of this stretching lineation getting smaller and getting thicker and also rotating. As this happens and it rotates, so you're actually destroying the ellipticity of the ellipse, if you like, which is actually representing the prominence of the lineation, of the visible lineation on the myelonitic plane. And there could be a plane which we have actually seen. There could be some planes which is distinctly myelonitized, and yet they have no foliation, no stretching lineation at all. And I think it's partially to do with the fact that this is a place where the earlier strain on the lineation and this one have evened out. So you've actually not able to get a extension characterized by quartz anywhere. Till You get into higher strain domains where now the elongation in this direction begins to take over, and then you get this. Now, what's important here? This is all gradations that we see in the field. So it depends on what you are actually going to be seeing. If we are seeing these zones, right, we will think that the lineation is down dip. If you're in these zones, you'll think that this was the extension direction, or this was the stretching direction associated with that particular myelinating zone. And yet, this direction has no kinematic significance either with respect to the previous deformation, nor with respect to what took place afterwards. It's only when you get to the highest strain zones of the last deformation that you can actually say with some degree of confidence that you've isolated the x direction that is associated with this myelinating zone. Now, to put it all together, lineations, these are integral to the definition of the reference frame on the basis of which we interpret any kind of shear zone kinematics. The concerned lineation you see is a stretching lineation. It's the x direction for that particular shearing event. For any simple shear component, it is important you need to understand if the x direction that you're seeing corresponds to the stretching direction of that shearing. For transpressional events, in fact, you can have mutually perpendicular directions. That's completely possible. Now, even without transpression, however, we need to determine if the visible lineation that corresponds to the stretching direction of that limit, or is it a result of cumulative strain? And in this case, that direction may be of no kinematic significance whatsoever. In fact, it's dangerous to make any kind of interpretation based on that kind of orientation. So therefore, any prominent lineation, this is the lesson that I've learned so far, is that just if I see a shear zone and I see shearing and I see a lineation on the exposed shear plane, I cannot and do not assume it naturally to be the stretching direction, which makes my job much more complicated because I'm never sure of what the kinematics are. It could be because I'm right. It could be because I'm a poor geologist. But the thing that I would like to say is that the message that I've been taking home for 25 years of failure of trying to recognize kinematics with confidence is that the evolution of lineations in ductile shear zones, it's actually a function of temperature, strain rate, and finite strain. So if you want to make a proper kinematic interpretation of these shear zones, you have to correctly identify the stretching lineation. And for that, you need to have the high strain zones or the highest strain zones and the high strain rate zones, if you can, of that particular deformation, zones in which all minerals are significantly elongated. Unless you do that, at least I would be reluctant to make any kind of interpretation. Before I end this whole meeting, and thanks to Tridip for organizing this, is the gentleman for whom all of us are gathered here. I knew him only as a teacher. I am 2 years junior to Parthoda and Hoshidda, who were here earlier. He also taught us just Precambrian geology, I think, is something that he did teach us. I don't think he taught us anything else. So he was a guest lecturer from ISI, used to come. And one of the things that I remember about him is in every class, he would bring us a sheet with a set of about 10 questions, which he would distribute. These 10 questions were not going to be answered in that class. It would be answered over the duration of the course, right? And he would ask more or less those questions in the exams of him, also, which was nice of him. But they were difficult questions, and you had to think about them. And what he taught was related, but not directly what exactly were the required answers. So you had to read to understand. Those who worked with him for their master's project, like Parthoda here, would know much more than me, but my interaction with him increased much more, manifold, after I became a faculty. I had attended a GSI field workshop with him in 1998 across the Eastern Ghats, and from then onwards, we've been very closely associated. He was my mentor in many senses, and even in times of distress, I would turn to Professor Dilip Saha or this gentleman here for any kind of advice I need. And for younger brothers, I turn to him, right? And he's the guy who knows how to pick me up when things go wrong. And of course, my students like Tridip are the ones who've kept me, sustained me to this day. But it all, I think, is because this gentleman was there initially that I wanted to do research, but I think he left us much too soon I wish he hadn't. Right, thank you. Yeah, I can take, but I don't think there will be questions. Yeah.
Just, it's not a question, observation. In your geological map, you showed mafic dikes.
I showed?
Mafic dikes
Did I?
in Rengali.
In Rengali?
Rengali province.
Mafic dikes?
Mafic dikes, you
There are mafic dikes, but I
no, you showed means in a legend.
With mafic dikes, maybe that would be there, yeah.
So now they are products of extensional setting.
Uh,
Now, in a compressional setting, how they would react to, in comparison with other rocks?
They're not related, because the Rengali province Chanukites, where we find the mafic dikes most commonly, these are all amphibolites. This is a Charnokite. Now, the thing is that the Charnokites, after they were emplaced, I think somewhere around 2.8 or so, I think they were recrystallized in the amphibolite fascies or upper amphibolite fascies. And the extinctional event took place somewhere in between the two. So there was a mantle derived influx together with some extension. These dikes are all folded now by these events.
They are not, no more mafic dikes, they are amphibolitic dikes.
They are amphibolites. They are mafic, but they're mafic, but they're not basaltic or doleritic.
Okay, okay.
So there is one dike which is doleritic still, but that has undergone only the D3 event. So there was something that happened even after all these Archean stuff. So it's not completely innocent.
Right, right.
So it's happened. Things like that have happened. Yes. Just had to say one thing. When I began on the Rengali province, it was with an MTech student who had his MTech problem there and a master's student who had his master's problem there. The MTech student is Surajit Mishra, who continued to do his PhD on the area, and the master's student is the guy who's asking the question.
I'm fortunate. No, sir. The thing is that it's always great to listen to your class or your talk. The thing is that we are live streaming this program. So one or
you didn't tell me that before. I mean, I should have been more careful about what I said.
No, it's absolutely fine. Now the thing is that one of my friend, probably you know him, Dr. Durga Prasad Mohanty. He's listening your talk, the Pune University. So he requested me, if possible, if I ask two questions. So he has written, I just read out.
It's possible for you to ask. Answering is mine.
Okay. So two questions. One is, in a transpressional or transtensional shear zone, how would you interpret oblique stretching lineations? One. Number two, how can stretching lineations help differentiate between thrust-related shear zone and strike-slip shear zones?
Between strike-slip and?
Strike-slip and thrust-related shear zones. Thrust-related shear zone.
Thrust-related.
Thrust-related
That
shear
should
zone.
not be a problem. I mean, the second one, taking it first. See, the way one would always do it is, if you find out the transport direction in the shear zone, look at the plane of asymmetry, right? And then with respect to the lineation, if you assume that to be the x direction, then you look at the section through the foliation parallel to that particular lineation. That's the classical way in which we all do that, and try to, understand what it would be. So if it's in a vertical section, you'll have to orient the section so that you know whether it's thrust or normal sense, right? Or whether it's strike slip. That is the case. The problem, of course, that I think now, I think is the problem with all this problem of lineations. If I'm seeing, I suspect a significant simple shear component when I see significant asymmetry, when I can understand that there is significant asymmetry in a particular zone. In that case, what I try to do is to get the vorticity axis, if I can estimate that. And I will choose the plane perpendicular to that to do my kinematic interpretation.
I don't know whether Durga is satisfied or not. Anyway, the first question was, in a transpressional or transtensional shear zone, how would you interpret oblique stretching lineations?
But this is not my work. This is Tikoff's and Green's and old work, actually.
Yeah, I think so.
It's a famous work. But anyway, I mean, this is that, it switches. In fact, you wouldn't get an oblique shear zone according to Tikoff's model. You'd get either this or that, I think.
By Tikoff and Fossen.
Probably, I forget. Tikoff and somebody else. Anybody interested in lines? Okay, 2 questions after lunch is not bad, actually. Okay, thank you very much.
Thank you, Professor Gupta, for your very thought-provoking presentation. Today's final lecture will be delivered by Professor Taposh Bhattacharya, retired professor of Calcutta University. It is my honor to introduce him, especially since I had the privilege of being his student. He is a distinguished educator whose teaching career at Calcutta University shaped generations of scholars. For over 40 years, he combined intellectual rigor with compassionate mentorship, bringing clarity and purpose to complex subjects. His depth of knowledge, combined with clarity of explanation, has consistently inspired students to strive for excellence. A truly multifaceted human being at his core, his patience, guidance, and encouragement have shaped not only scholarly growth but also personal development beyond academics. Even after his retirement, his commitment towards teaching remains unwavering, with his continued association with Aizer Berhampur. It is through such commitment and mentorship that Professor Bhattacharya leaves a lasting and meaningful impact on all who have had the privilege of being his student.
পকেটে পাইখানা যেখানে Thank you all for being present at this very late hour. And I'm sure since the morning you have been enriched with really very important issues of general problems about sciences, mantle, then talking about shear zones, and then a very complex problem of how mutational ridges form or their magmatism. Compared to that, what I'll be telling you is an old man's view of old style geology on old rocks. I have one distinction in this audience. I am the oldest man here. And today, I was just thinking while having the lunch, very sumptuous, that today I am completing a full cycle of my professional life as a geologist. My first ever professional talk in this country was held in this department in 1980s, when I was a fresh PhD from some other place, and Dilip, Dr. Dilip Saha, 1 year senior to me, a very intense person, he made me give the talk, and that was the beginning of whatever my journey in Indian geoscience. And surprisingly, this could well be my last talk in geology in India. And that too, very unfortunately, in memory of Dilip, who introduced me as a speaker in India. It's very difficult for me to talk about Dilip. My voice might choke. So the topic I chose is more keeping in mind Dilip Saha, Dilip as an outstanding field geologist. I have the privilege of accompanying him in 2 conducted field trips in Eastern Ghats and Shinghom. And then he forced me into a field trip into Western India, into a greenstone belt. And all the interactions that I ever had with him on geology was on very particular issues that I can see in the field. Nothing like the big models or anything like that, argument, anything like that.
And it has been so intense that in one of the guided field trips in Eastern Ghat, conducted by ISI, where Michael Brown and other people were there, and I and Dilip was constantly arguing and talking about that, and Michael Brown pointed to an outcrop and said something. Dilip said, but there is an alternative. I said, we must remember that. Then Michael Brown said, when you two are talking, I accept. So that was my interactions with Dilip. There are many other occasions when we have interacted. He once really shouted at me for only once when I was dilly-dallying to be a joint guide of one of his students. And so sad that he left, leaving the student on me, unfortunately. So the name has field expressions. It is my tribute to his passion for field geology. And the work is very old. It is a confession. The work was done in a single day, in a 4-hour time, in a place near Chitradurga in 1988. So we saw the rocks. I will take you in the field trip. It's a slideshow on that outcrop proper and narrate what is my story about it. And we all developed in a single day. I was accompanied by a very distinguished field geologist, Dr. Mohan Chand Bardal. He was at that time teaching in Jogmayadevi College. We had no money. We walked down from Chitradurga. Chitradurga was a sleepy town, on foot hunting for rocks, no GPS. And all of a sudden we bump on a rock. They're called chatans, flat top, zero relief on the ground, peninsular gneiss. And I was a poor teacher, and I wasted one full reel of Kodak transparency on that outcrop. So what I will be showing you, some of the selected transparencies. At that time, I was a member of faculty in Allahabad University. Our field trip was supported by this. Field means many things to many people, okay? And field has multiple facets. There are people in India to which I used to be a subscriber in earlier days. Unless you stay in field for 2 months and doing this, you're not doing that. That's not right. And I will show you one meaning of field. I hope Dilip won't be angry, from this cartoon. Read it. And the last photograph picture is fantastic. And I have found people in real realms of geology who subscribe to that. When you have seen one field, you have seen them all. So with that, I jump into the outcrop. As you walk into the outcrop, this is where Chitradurga is, just for oriented. This is your first encounter of the rocks. Black and white rock, and there is some light, that's why contrast is not very high. If you look at it, there is a straight vein. These are quartzo-feldspathic veins, almost granitic composition, not much of mica. Then there is a vein which has very peculiar geometry. Then there is a vein straight, but kind of disrupted. So between these two veins, something is happening. If I take a quick look, we see there is another set of plane which is oblique to this gneissosity. And you see the plane is kind of mimicked by this structure. My whole talk, all the slideshow, will be on the structures in these things. Then another part of the outcrop. When I first showed it to someone, very honest gentleman, he said this is a crenulation cleavage. In 1988, possibly, we Indians had very little options. But the question I asked, if you call it a zonal crenulation cleavage, like these zones, there are fold hinges, white is quartz, feldspar, black is mica, then there is almost same proportion of mica, quartz, and feldspar that they are stretched, elongated. But most of the zonal crenulation cleavages are product of pressure solution removal with the presence of water. We are looking at gneiss, peninsular gneiss, at least amphibolite. And if you look at the geometry of the vein, that is spectacular. This part is outside these zones. It is giving you a thickness. If you come in these limbs, they are very much thin, stretched. And look at the hinges, they are kind of flattened. I put some imaginary lines on it. Could that be small shear zone, dextral in sense? And that could be created by a major shear zone whose foliation is parallel to shear zone, as Dr. Gupta was saying, something like that. And because of this shear, we develop this sinistral in plan folds. So the major shear outside is sinistral. And as a result of this sinistral, we are having antithetic dextral fold restricted within the shear zone. Now, you can see the proportions are almost the same in the limbs, in the long limbs and the short limbs. There is hardly any short limb you can see. This is all hinges. And main shear sinistral, antithetic dextral. Very nostalgic lens. I am still having it. My first day of geology was marked by the purchase of this lens in 1972. So I'm still holding on to it. So this is we thought of. We have this particular sinistral shear. Don't worry too much about these infinitesimal strain ellipse shapes. It cannot be drawn. But general, if it is a simple shear, 100%, this is the expected orientations. And there is a dextral one. And I tried to play with my imagination. These are the blocks white with the hinges and the short limbs. And these are the intervening zones where you are having the limbs thickened. So I put it at subsidiary shear zones, sinistral, and these are antithetic dextral one. Spectacular example. It's not fish hooks. I see outside the shear zone, these shear zones, this is the true thickness of the vein. The vein gets very thick at the hinge, and these long limbs got extended. And look at it, squint your eyes, extremely extended. So I enhance it. So definitely imagine it is about 3:30 in the month of June, very hot, and we are not sweating out of this heat. We are sweating out of excitement and drawing sketches on the field. And this is what I believe this is happening. It's incredible. And then, oh my God, look at it. If I can draw it, this is the long limb of a fold. It comes, it goes, it comes, a big sinistral, a small sinistral, together making an M fold. This is the long limb. I enhance it. This is it. These transparent ones are the long limbs. These patterned ones are the short limbs. Imaginary, it might have started something like that and got flattened at the hinge and the short limbs, and the long limbs become longer. So you not only have a dextral shear along these planes, but to make the hinge thick like that, a simple case of simple shear, it is very difficult to do that. So you might have to have some kind of shortening perpendicular to these things. I did not spend much time after 1988, okay? Only once I did it in 2005 for a talk somewhere else. This really took the rug from beneath my feet. To be very honest, you can see the upper part of the shear zone, the sinistral shear zone, the lower boundary like that. I made them in two different colors. We'll come to that. For two completely different kind of microstructure it is showing. This is the dextral one. I'll come back to that. Now, very simple explanation. I have very open fold. If you track this tracer I put, the band is very wide. The folds are very open, not that symmetric. As I move in this direction, the orientation of the band changes. The folds become tighter and the band width becomes smaller. If I accept for statistical reason the probability of these bands of equal length, equal width to start with, then it might indicate this is an older version of this newer one. So it started something like that. With progressive simple shear, these are bound to rotate. But you have to have some other thing acting on it to make the band boundaries come closer together. So you have to have some kind of homogeneous or heterogeneous shortening parallel to it. So this is one part of it. Then, again, I am trying to show what I am implying there. You have to have a compression perpendicular to this band boundary. The other thing is unbelievable. Look at these triangular things, like the short teeth. The vein has a straight bottom, but the top is matching as if there are some voids created. And the vein is possibly seen shearing, because void cannot be left. So when the shearing taking place, the vein material came and filled up the vacant spaces with the triangular spaces there. Well, this instantaneously hit us that we are looking at something like a bookshelf in a large scale. This is a bookshelf, very bad bookshelf. The bookshelf top, you never touches the book, okay? This is a stolen picture. So, and I tried to show what I mean, the difference between our observations and the books. The boundary between the two books in normal terms is a fault, no ductility. The only difference between what we are seeing there and this one is in between the two books, there is a ductile shear zone that makes the vein or the band stretch. Well, I want to make you see it very better. This is, think of it, a 6-volume work, and there is no top shelves, either mark it like that. This is before deformation. This red line marks the top of the book, and you can take is the equivalent of the upper shear zone boundary. This is the lower boundary of the shear zone. I kept the red book straight to give you an idea was the pre-shearing width of the shear zone. And you see, to start with, because this is a rectangle, when it rotated by 10 degrees, it is more like the diagonal came to the top, then the shear zone boundary expanded. If you have to do it like a rigid book, you have to do it like that. But if I give it a larger amount of rotation, the shear zone boundary moves inward and the shear zone width drops. So if you have the books in a bookshelf model, perfectly rigid, and if you like to rotate, then you have to think of some mechanism of moving one shear zone wall close to another, unless you are creating gaps, big gaps. And look what is happening. The more the shearing, the more these triangular gaps. So when the shearing was taking place, at least some amount of book shape like rotation took place, and the vein material occupied this. It's incredible. When I saw it, I could not believe that. It is unimaginable. Now, this is a very similar model with one major difference. Here we are keeping the books not rigid, but deformable. Each book is undergoing homogeneous deformation. So the books are getting longer and narrower, so that the distance between the two shear zones remains the same. But even if a slight movement generates these triangular gaps. So this is about 30-degree rotation. This is about 60-degree rotation. Note, the distance between the two walls, the width of the shear zone is not changing. It can be only happening if you are looking at a bookshelf when the bookshelf itself is behaving ductilely. Otherwise, it is not possible. Taking a closer look at that, the bottom of this thing, this is the ideal bookshelf thing. Very nice straight edge, straight limbs triangles. But what we see like this. So it is deviating for this right angle triangle, which would have happened had the books been perfectly rigid. So as it rotates, it not only extends, it is undergoing some kind of shearing displacement within it. The two dextral antithetic shear is giving it like that. So the shear, the block in between is getting an opposite direction. As a result, this angle, which should have been like that, but this book moved upward, this part moved down, so it has turned into this particular geometry. So now we are including a bookshelf with books rotating, which are extending at the same time possibly undergoing simple shear parallel to the antithetic shear zone boundaries. So you can see the rotation I calculate is about 43 degrees. So this is deformation of each book is a combination of counterclockwise rotation, naturally, of the main stencil, stretching along its length and shortening parallel to its width. I am using constant area. This is just a standard thing, okay? There is no way to check it. Making it standard area, those who are modeling it will help them make it easier. Simple shear, subsimple when combined with B above. When I was talking about that, I never knew the word subsimple shear. Okay. So this has enhanced the rotation of the short limbs within the book, making the within book folds tighter, and after initial thickening, finally thinning of the short limbs and complete obdulateration. So these are the possible end-member cases that I was discussing. As with the actual books, the domains of rocks that are books do not deform at all. No change in area, no change in shape, but undergo rigid body rotation. The walls of shear zone should come closer together. And there is no change in the angle between the short limbs of the asymmetric force, so they'll just rigid rotate. So folds will not get tighter. This is what we have been talking about. Rigid thing, walls are moving, rotating like that. The second possible case is possibly the most complex and more applicable to what I have been describing. The domains of rocks will undergo constant area. I made it constant area red, okay? This is my imagination. It will still apply without being constant area. The whole geometry will not change much. Finer details will be modified. With proportionate length parallel extension and length perpendicular shortening. This will make asymmetric folds tighter, decrease in angle between the short limbs and the domain boundaries. As it ties the domain boundary, the two dextral shear zone, the angle will drop, making the short limbs very nearly parallel to the boundaries and hence subjecting to stretching. This overall flattening will lead to thickening of the hinge and near complete obdulateration of the short limbs. Now this is a very adventurous statement. Depending on the rate of stretching parallel to the domains with respect to the rate of shear along the main shear zone, this one and this three, if the two the rates match, then the shear boundary, shear zone boundary will remain straight. It will not move this way, that way, because the more it rotates, the effective length, the width of the shear zone remains constant. If one is slower, it will move that. If it is enlarging, it will move back. This is what I meant to say. So these are taking as rigid, rotating, something like that. And this is just to remind you the scenario, these angles. Just to remind, the flattening part is difficult to overlook. The fish hook I showed, it is impossible to attain from this thickness unless I have a hinge. So same flattening will make the limbs thinner and hinge thicker. And the third, which is a very idealist one, as we see in felspars, oh, this is not we do see, the first one. Deformed by simple shear parallel to their boundaries, antithetic. Let me show you this picture. Now, it seems rather contradictory, those who are very keen observer. We are saying these boundaries, one book, another book, is a dextral shear zone because the whole shearing is sinistral. But if you put that dextral shear zone across this line is moving that way, that line is moving this way, so that will generate a simple shear which is sinistral. You notice me, if you have to make it a dextral shear zone, which way this block will move here? Downward. This block will move upward. Again, this margin of the block will move downward. So it will change the shape as if it has undergone a sinistral shear. Now note what is happening. There is a short limb, I have not drawn the long limb. The short limb, I calculated it, it is done accurately. It will rotate and it will become thinner. Now first initial rotation will make this tip go out of the shear zone boundary. Shear zone will expand. So if you have a shear zone of varying amount of shear, then in one part the shear zone will bulge out, one boundary, another part it will drop. If you give it more shear, this band has becoming thinner. It has come down to the same boundary will come like that. If you are having a simple shear affecting them. My personal impression now when I looked into it about 40 years back after, that possibly the things that I have been seeing there, I have seen there only for once, is a case which has this rotation with extension plus some amount of this shearing. Otherwise, these changes this change in the angle here is difficult to explain. If it is increasing in length, the angle will change, but it won't be that tight. As you can see, I did mathematically drawn thing. You see how the same thickness limb becoming thicker here. It is the same line I started with before I did deform with some just graphic program. So, this is the conclusion, and I have not made any change in the conclusions. I leave it to you to correct me. This is an old conclusion from an old man, 1988. I cannot believe many of you are possibly not born then in the audience. So, structure within shear zone developed in rocks is controlled by the early fabric. You have been talking about early lineations. Shearing forms asymmetric folds. These are buckles. Professor Mondol is there. He told us in 2004, you can have buckle folds following Ghosh and Sengupta 87, 88. Early fabric, the longer limbs of which become zones of subsidiary shear antithetic to the main shear. Very simple, everyday observation under microscope with feldspan. Such individual fold-bearing rock slices behave like books in the book-shelf model. Generally, I was very cautious, generally. Constant area flattening deformation within the books modifies the folds to have very thickened hinges, short limbs, and very thin. You can take out the constant area, still it will have the same effect. The subsidiary antithetic shear zones terminate near the main shear zone boundaries, two interesting ways, by gradual decrease in the amplitude of the folds within book folds, or more spectacularly, abrupt termination with this. What he meant by this 4A is this one. If you look at this one, you see this shear zone, this particular book, the block dies. The foliation outside, the amplitude of the folds gradually dies and gradually vanishes. So back to the conclusion again. By gradual decrease in the amplitude of the within book folds, or more spectacularly, by abrupt termination with the creation of triangular spaces. So this is the conclusion of it. We are paying homage to Dr. Saha, an avid teacher, avid reader, and I talk a lot about books. And books are now becoming a point of interest to many people. What are books? And last week I came across a cartoon from a Norwegian cartoonist, Glassbergen. He made a nice cartoon about books. This is a talk between two teachers. So I thought it is befitting while we are talking about bookshelves, we should be aware what the book is all about. So with this very short slideshow, I don't know whether any substance in it, I pay my tear-shocked tribute to Dilip, my friend. Thank you. I planned for half an hour actually.
So as expected, very, very stimulating and making me think differently now. Now I'm just wondering, in this case where the shear zone wall, just by virtue of the geometry, if you take the bookshelf, for it to work, the variation in thickness of the shear zone has to be a natural consequence. In that case, the part where suppose the shear zone walls are rigid and not actually deflecting.
The shear zone walls, the country rocks.
The country rock is rigid. So the material in between now has to accommodate the space that is there. So when
then the books will have to adjust themselves. They cannot push it up.
Right.
They cannot go down, the void will
So
be
they must
created.
internally deform.
They will be strongly internally deformed. We'll
So
have to.
in what case will we call the deformation general shear then? In the case where it's actually, there is an element of change in weight, that means there is a component which is perpendicular to the shear zone wall.
That will make the books rotate faster and longer. They will become longer. Because
Definition wise, definition wise, will we call that general shear then?
If you're talking about the whole domain,
then not.
There is. But
then
there,
it would be, right?
Yeah.
I mean, yeah.
But within it, because as I was saying, when you look at the antithetic dextral shears, they are actually subsimple shears. I am appealing to a flattening and a shear. So that is actually domain of subsimple shear within. But I think we are all aware. I drew these things, you have seen possibly the name X1, X2. This is from, what's this called? I forgot his name.
Hagenfossen.
No, Hobbes-Means. This is the Means paper.
Mm-hmm.
Internal coordinate, external coordinate, complexities. I just wanted to show, because there will be students, I was told, that if you look at the broad sinistral shear zone, the infinitile stainless is going like that, because you are compressing like that. But within the dextral thing, it has rotated 90 degrees, because the two shear zones like that. So when you talk about strain, it is geographic coordinate bound. You can talk about a large scale strain. You talk about a small strain, say in a quartz ribbon, completely different could be something like. And you already mentioned about two types of strain cancelling each other out.
No, just one final question on this. This is just playing a devil's advocate. The variation in thickening you're seeing, because it's a Chatan outcrop you mentioned. So you can't actually see, you're not seeing the third dimension.
No, one thing is that I did not mention. I have time or not? I think I have time. Yes. I don't expect you to see that, but I think I see it. If you look at it, this is the vertical relief of the thing. Not more than 6 inches, 15 centimeters. Wherever we could see, my note says they are all vertical. That means the planes we are looking at, if it is a shear zone, you are looking at a profile section, horizontal. That's why there is so consistency in the angular relations, something like that.
So you're lucky enough to get the profile section on this outcrop.
Exactly. It's the whole thing. It's a 50 meter by 75 meters whole profile thing like that. When you first saw it, I thought of sharks inside the water with the dorsal fin coming out. And then I get brought back to my senses. I saw this is what is happening. In between the books, we have the triangular pits, and the vein is sin shearing. So the vein came in and filled it. And the vein that got folded, the earlier diagrams are possibly earlier. So there is multiple injections of thing. And the one that shows so many kinds of folds, this veil is possibly the oldest. It has recorded almost all the strain that the foliation, which possibly I think is also an earlier myelonetic foliation. Though I could see the grain size, that's why I did not describe, I'm calling it an ice. But this could be also some myelonetic, but it's also a shear zone related thing. And that is quite common, as someone was saying today or here, that you have repeated phases. You are saying that thing, repeated phase of shearing like that, something like that. And these are buckle folds, okay, because of difference in rate of movement will create compression. So that's why I'm giving you all the geometry, something like that. So I thank you all for giving me this opportunity, and thank you for listening to me.
Thank you, Professor, for a very engaging lecture. With that, we have neared the ending of today's program. On behalf of the organizing committee, I extend my sincere gratitude to all the speakers for delivering such insightful and thought-provoking lectures. Their valuable contributions have made this event truly enriching for all of us. I would also like to thank our respected faculty members, researchers, and students for their enthusiastic participation and engaging discussions, which greatly enhanced today's session. Our heartfelt appreciation goes to the Honorable Director, Honorable Deputy Director, Dean, and the administrative staff of ISI Kolkata for their constant support. We are equally grateful to the Security Department, the personnel of Electrical Unit, the Reprography Unit, the Estate Office, and the Accounts Department for their assistance in ensuring the smooth execution of this program. A special thanks to the organizing team and volunteers whose dedicated efforts behind the scenes made this event possible. I warmly invite you all to join us for tea outside the hall.
We would also like to inform you that the museum is open for visitors until 5:30 p.m. Please do visit. Also, with that, we conclude today's session. Thank you all for being a part of this enriching event. Thank you.